मंच एक खुला मंच है, आए जब भी चाहे। किशोर मंच एक खुला मंच है, आए जब भी चाहे। हर किशोर को मिलेगा अवसर, खुलती जाए राहें। आए जब भी चाहे, आए जब भी चाहे, आए जब भी चाहे, आए जब भी चाहे। हो कला सामाजिक ज्ञान, भाषा गणित या हो विज्ञान, कठिन नहीं है विषय कोई भी, करो जरा सा ध्यान। हो कला सामाजिक ज्ञान, भाषा गणित या हो विज्ञान, कठिन नहीं है विषय कोई भी, करो जरा सा ध्यान।
ये है
किशोर मंच।
In the last lecture, we discussed the motion of charged particles in electric and magnetic fields. We found that high energy charged particles coming from outer space are trapped by the Earth's field, and they form two belts known as Van Allen radiation belts. The important thing is that these particles are trapped and they do not reach the Earth's surface and do not therefore harm life on the Earth. I said that we shall start with magnetism today, but I think magnetism will take in the next lecture. In this lecture, we will take a topic which we have still to do, that is magnetic force on currents. We have already seen that an electric charge moving in a magnetic field experiences a force called Lorentz force. That force is given by F equal to q v cross b, as you know already. The emphasis is on moving charge, because if the charge is static, then the magnetic field has no force on it. Since the magnetic force on the charged particle is perpendicular to both v and b, it does not change the magnitude of v. It changes only its direction. That is, if the particle was going in this direction, then the magnetic field makes it move around the lines of force. It does not change the magnitude of v, it changes only its direction. This means that the kinetic energy of the particle is not changed, but its momentum does change. Also, since the force is perpendicular to the particle's velocity, no work is done. The magnitude of the force we have seen many times is q v b sin theta, where theta is the angle between v and b. If the particle is moving along the field, then sin theta is 0, and therefore, there is no force experienced by the particle. That means, if a particle goes in a certain direction undeflected, it does not mean that magnetic field is there. The magnetic field may be there, but it is parallel to the direction of motion of the particle, and therefore, does not affect it. If the current is uniform flowing through a wire of length L, then the force on it is F equal to I L cross B. You look at this, d F is equal to I d L cross B. If I is constant throughout the length of the wire, then it becomes I L. So, the force becomes I L cross B, that is, if the current is uniform. And what does it do? You see L crossed B. So, if this is the length going up and B is magnetic field going in, then you can work out by our old friend. Who is our old friend? The right hand screw rule. So, you can work out that if the length is up, the magnetic field is going in, then the force is in this direction. And this is also given by another mnemonic called left hand rule of Fleming's. In this case, you extend to find the direction of motion of the or the direction of force on the current, you extend the left hand fingers in this way. This finger represents the current, this represents the magnetic field. That means, if the current is in this direction, if the magnetic field is in this direction, then the force on the current is in this direction, that the current would move. If a movable conductor, then it will move in this direction. This is the Fleming's left hand rule. But my advice to you would be, do not worry about the Fleming's left hand and right hand rules. What you worry about or what you learn is the right hand screw rule. If you right hand screw rule, if you remember this rule, then you can always find the cross product L cross B by using the right hand screw rule, and you will never make a mistake. Now, suppose we have two long straight currents A and B, and they are in the same direction, they are parallel to each other, and the distance between them is d. The magnitude of the magnetic field due to current A at distance d from it, which we found last time, is B A. The field at B due to A is B A mu 0 I A by 2 pi d. This formula we derived in the last lecture or maybe a lecture earlier. This field will exert a force. Now, there is a field, there is a current, therefore, there must be a force on the conductor. This force is I B L B A. L is the length of the wire and I B is the current in this, B A is the magnetic field on this in this direction, and therefore, you can work out the force. The force is mu 0 I A I B L by 2 pi d if I substitute the value of B A. And you can see this is symmetric, whether I start with A or with start with B, the force on the two will be the force that these two feel, the mutual force is mu 0 I A I B L by 2 pi d. And if I calculate the force per unit length, it is F A by L, which is mu 0 I A I B by 2 pi d. So, that is the force between two wires, and you can see that this force on B is in this direction, on A it is in this direction. That means, the two are mutually attracting each other. So, two parallel currents attract each other, and if one of them is negative, then say anti-parallel currents, one going like this, the other going like this, then there is repulsion between them. And this formula allows also to define an ampere. So, suppose 1 ampere current is going through these and the distance between them is 1 meter, then we can find the force, and that force would define the unit current called ampere. So, we find that the force per unit length would be mu 0 by 2 pi equal to 2 10 to the power minus 7 Newton per meter. So, an ampere is defined as that current which, when flowing through two infinitely long parallel wires placed at a distance of 1 meter from each other, would produce a force per meter between them equal to 2 10 to the power minus 7 Newton per meter. That is the formal definition of an ampere. Let us take an example. A long wire carries a current I. So, there is a current I. A charge q is moving in a direction parallel to the wire with velocity v. So, we have a particle moving with velocity v. Find the magnitude of the force on the charge. Simple. Remember that a moving charge is equivalent to a current, and these currents are parallel, therefore, there will be attraction. You can find what the attraction would be using the formula, but the basic thing is that this is a current in this direction, distance d is given. So, I can always find out the force between them, and this force will be of attraction. This particle would be attracted by the current. In the above problem, what should be the direction of motion of the charged particle, so that the force on it opposes gravity. That means, what I require now is that I want the force to be in this direction, so that the gravity which is in this direction is opposed. So, obviously, we must be from right to left instead of from left to right, it must be from right to left. So, that the two currents are now in the opposite direction, they are antiparallel, therefore, there will be repulsion. So, the force on this particle would be upwards. I can balance this by the weight of the particle, and I can get the necessary velocity. So, that is what I have done. It is simple, you can do it. Now, one of the instruments that you must have used in the laboratory very often is a galvanometer, moving coil galvanometer. So, we want to now discuss the structure of a moving coil galvanometer. What will be the principle? We will suspend a coil in a magnetic field. There will be force, because the coil will carry current. In this current here is in this direction, here it is in this direction. So, there will be forces, they will constitute a couple, and this couple would tend to rotate the coil. This will be opposed by the suspension. When the two balance, you get the relation between the current and the deflection. That is the principle broadly. So, I will explain here. We have a coil here. This coil, suppose it is perpendicular to the magnetic field, then what happens? You can work out, now you know the right hand screw rule. So, you can work out that if this is the direction of the current, then the force due to the magnetic field in this direction would be outwards, and on this side it will be in the opposite direction. So, we have two equal and opposite forces, and as you know, they form a couple. The arm of the couple is equal to the distance between these two forces. So, we have a couple, the arm of the couple is equal to the width of this coil, which is B, and the force is ILB. The couple would be therefore, or the torque therefore would be ILB times the arm of the couple, that is the distance between the two forces, and therefore, the torque is IAB, where A is now the area of the coil, which is L into B. So, if there are n turns of the coil, then the torque is NIAB, and this torque tends to rotate the coil, and the suspension opposes this motion, and therefore, after some deflection the two come into a balance, there is equilibrium, and at equilibrium, if C is the couple per unit radian of the suspension, then C theta is equal to NIAB, and from this I get I equal to NAB by C into theta. So, I turns out to be proportional to theta, provided A remains constant. We will see how we can make A constant, and why, if A is not constant, then this I is not proportional to theta. You see, I have shown you here 5 positions of the coil. Here the coil is parallel to the magnetic field, the plane of the coil is parallel to the magnetic field, and then the two forces are in the same line. So, the couple is 0, torque is 0. Here, when the coil is perpendicular to the magnetic field, the two forces are equal and opposite, and the distance between them is the width of the coil. So, we have the maximum torque. Here the torque is again 0, here again maximum, here again 0. So, the torque changes, and therefore, we cannot say that I is proportional to theta, because A is not remaining constant. How do we make A constant? We must devise a way in which the coil has the same area perpendicular to the magnetic field all the time. How do we do that? We embed a core in the coil. This core is of iron or some material which has properties of iron. These are ferromagnetic materials, and they attract the lines of force or the magnetic field lines. So, they attract the magnetic field lines, they concentrate in the core, and therefore, the coil is always, the plane of the coil is always perpendicular to the magnetic field, and therefore, the torque is constant, and therefore, if the torque is constant, then this formula I equal to n a b by c into theta gives us I proportional to theta. So, the deflection of the coil is a measure of the current going through the coil, and this arrangement of measuring current or estimating current is called a moving coil galvanometer. A galvanometer is suitable only for detecting currents. That is why it is used in experiments with meter bridges and potentiometers, where the current is only to be detected and not measured. You must have done some of these experiments, and therefore, you would know that there we just find out the point where there is no current, and we just detect current, we do not measure it, we do not need to measure in those experiments, and therefore, we use this moving coil galvanometer. If we want to measure current, then we need an instrument which has a very low resistance, so that the potential drop across it is very small compared with the source voltage. Let me explain. Suppose source voltage is V, and if this galvanometer has sufficient resistance, then there will be a potential difference across it, and that means the current through the circuit will be affected, but we want to measure the current. So, we cannot disturb the quantity to be measured. That is a general principle of physics. So, what do we do? So, we devise an instrument so that it has very small resistance, and therefore, the potential drop across it is much smaller than the source potential. And this arrangement is called an ammeter. An ammeter is an instrument which measures current. And how do we get the small resistance? We use a shunt. Here I show the arrangement. Galvanometer has certain resistance, then this shunt, a very small value shunt, is put in parallel to the galvanometer, and this reduces the resistance of the galvanometer suitably, so that we can convert this into an ammeter. Similarly, we can convert galvanometer into a voltmeter. What is the purpose of a voltmeter? What is the job of a voltmeter? Voltmeter must measure the potential difference in the circuit, and if it is to measure potential difference, then it should not disturb the potential difference. That means, there should not be any potential difference across itself. That means, it must have a very high resistance, so that no current goes through it, or very little current goes through it. So, we use a very high resistance in series with the galvanometer, and this instrument is called a voltmeter. So, that over the voltmeter itself there is very small potential drop. So, that the potential drop which we were supposed to measure is not disturbed. Let us take an example to understand what is happening. A galvanometer has a resistance of 19 ohms. It gives a full scale deflection for a current of 0.5 amperes. If it is to read a maximum of 10 amperes, what should be the resistance of the shunt? So, we have a galvanometer resistance 19 ohm. We want to convert this into an ammeter, so that the ammeter can read 10 amperes of current. The full scale current in the galvanometer is 0.5 amperes. So, it is obvious that 9.5 amperes should go through the shunt, and since they are parallel, the potential difference across these two must be equal. So, 19 into 0.5, 0.5 is the full scale current in the galvanometer. So, 19 into 0.5 is equal to the value of the shunt S into 9.5 amperes, because out of 10, 0.5 can go through this, 9.5 must go through this, and this gives S equal to 1 ohm. So, the shunt value is 1 ohm. Suppose the galvanometer of the last example is to be converted into a voltmeter with a range of 100 volts. What must be the value of the resistance to be attached in series? See, the fall of potential across the galvanometer is 19 ohms into 0.5 amperes, which is 9.5 volts. So, up to 9.5 volts it goes through the galvanometer. The rest 90.5 volts must go through this resistance, must fall across this resistance. So, if the current remains 0.5, because that is the current going through the galvanometer. So, if the current is 0.5, if the potential drop is 90.5 volts, then the resistance must obviously be 90.5 by 0.5, which is 181 ohms. So, if you apply simple logic, you can decipher such problems of converting galvanometers into ammeters and voltmeters. In the last lecture, we found this quantity q b by m, which is the cyclotron angular frequency, and its dimensions must be t to the power minus 1. It is a frequency, therefore, it must be 1 by t. So, how do we show that q b by m has dimensions t to the power minus 1? The best way to find the dimensions of q b is to remember that f is q e b. So, q b is simply f by v, and q b is f by v, and there is m. So, it is f by m v. So, we can find the dimensions force by mass into velocity. Force is m l t minus 2, mass is m, velocity is l t minus 1. So, from these two you get t minus 1. So, it is easy to show that q b by m, the cyclotron angular frequency, has the dimensions t minus 1. We have seen that a current loop exerts magnetic field at its center. Last time we saw that if we have a loop of current, then there is a magnetic field which goes through the center of the loop. That means, I told you that loop acts like a magnetic bar or bar magnet, and therefore, it has a momentum, and dipole moment of the loop is given by I times A, where A is the area of the loop, that is L into B, it is the area of the loop, and I is the current going through this. So, if I have a loop with area A and current I, then it acts like a dipole whose dipole moment is I times A. Now, what happens if I place such a loop in a magnetic field making an angle theta? Then what happens? The magnitude of the moment of magnetic field parallel to the plane of the loop is b sin theta, and so the force acting on the current I in the arm of length L is I L b sin theta, and therefore, the torque is I L b sin theta into b. The torque is these two equal and opposite forces multiplied by the distance between them, which is b. So, L into b is area. So, it becomes I A b sin theta, and I A, remember, is the magnetic moment, we just magnetic dipole moment of the loop. So, therefore, the torque on the loop placed in a magnetic field at an angle theta is I A b sin theta or m b sin theta, and in vector notation this torque becomes m cross b. Remember that an electric dipole in an electric field experiences a torque which tends to rotate it, that is equal to P, the electric dipole moment of the dipole, into must be E. So, the torque on an electric dipole in an electric field is P crossed E. P is the dipole moment of the dipole, and E is the electric field. So, what have we learned in this lecture? We have learned that if there is current and there is a magnetic field, then the two interact and there is a force on the current, which if the conductor is movable, will move the conductor, and the force is of course I cross B into the length of the conductor, and you can always find the direction in which the force will act, or if you prefer, which I do not, if you prefer, you can use the left hand rule of Fleming's. This is the current, this is the magnetic field, and this is the direction of force acting on the conductor. And if we have a loop in a magnetic field, then this loop tends to move, and from the and the suspension of course, opposes this, and the equilibrium is achieved at a certain deflection. This deflection is a measure of the current going through the instrument. This instrument is called galvanometer, which we can convert into ammeter for measuring currents or voltmeter for measuring voltages. In the next lecture, now we shall take magnetism.
I am Anuradha Mathur. I teach physics at Modern School, Vasant Vihar, New Delhi. Today we will be talking about the magnetic field associated with the Earth. It has been long established that the magnetic field around the Earth can be experimentally determined, accurately measured, and we are going to see how some of these relevant and important elements are found and defined. Let us consider the globe. It is a toy globe, and we are going to see how geographically, how do we talk about different portions and positions on the Earth. And if you can see here, there are latitudes and longitudes marked. So, it is easy to talk about a location in terms of the longitude passing through the Greenwich. All these are marked as east and all these are marked as west, and the equator, the axis of rotation of the Earth is inclined at a particular angle. These things are known facts, geographically established facts. Pictures from the space have shown that the axis is inclined. How do we know that there is a magnetic field associated with the Earth? We have a freely suspended magnet, and if we ever were to keep it in a way that it is ready to move about a vertical axis, as in this case, it will always rest in the north-south direction. This north-south direction is associated with something inside this. That means, we imagine a dipole to be inside the Earth. The dipole, where are the poles associated with this? Some of the known facts about the Earth's magnetic field are that the south of the dipole imagined inside this is somewhere in the northern section, that means somewhere over here, and the associated north pole of our magnetic dipole is towards the south. Where exactly this is has been seen by study of field lines, and it is found that the magnetic south pole lies somewhere in northern Canada at a location marked here, which is 79.8 degrees latitude and about 71.4 degrees west longitude. So, somewhere around here you will have the pole. That means, not exactly coincident with the geographic north, which would be passing through the axis here. Some more facts known about the magnetic dipole inside the Earth are that it has a dipole moment of around 8 into 10 to the power of 22 ampere meter square, and the dipole axis is obviously inclined, joining the two magnetic poles here to the axis of rotation, and this angle has been found to be 11.3 degrees. Also, on the surface of the Earth somewhere you find that the magnetic field has been obtained somewhere around 10 to the power minus 4 Tesla. What causes the Earth to have a magnetic field? For a long time it was thought that there was a magnet inside it, but that original thinking is now redundant, and conventionally today what we think about the magnetic field, we say it is due to the movement of molten fluid inside it, and so the convective currents that are in it, fluids such as molten iron, molten nickel, and that is what is said to be responsible for Earth's magnetic field. Having said that the Earth's magnet inside the magnetic field is generating the two poles, so it is a dipole. Can we estimate the value of its magnetic moment? Well, sure we can, by using our old expressions that we have been using for magnetic dipoles or current carrying loops. Let us see how we can do that. Let us do this estimation by saying that at the equator the magnetic field is 0.4 Gauss and the radius of the earth is 6.4 into 10 raised to the power of 6 meters. And using our expression which we used for the dipoles earlier, mu naught m upon 4 pi r cube, we get this value for m to be equal to 1.05 into 10 raised to the power of 23 ampere meter square. This value is consistent with the value that has been experimentally determined, which comes out to be approximately 8 into 10 raised to the power of 22 ampere meter square. This consistency not only establishes that we have to take and treat the Earth's magnetic field as on account of a dipole, even though there is no magnet inside it. So, let us now look at other factors which are necessary for its description, and before we do that we are going to do some definitions. Definitions of the type that we are going to talk about the geographic axis as the line joining the north pole and the south pole as geographically established. We are going to talk about a magnetic axis as the line joining the magnetic south pole and the magnetic north pole over here. We are going to talk about a geographic meridian which would be a plane passing through this axis. So, at a location the geographic meridian would correspond to the longitude passing through the axis. So, a plane of this order. So, for every latitude you can imagine a geographic axis passing through the axis of rotation and the location at that point. What would then be the magnetic axis? This magnetic axis would be the line joining the magnetic dipole and a plane passing through that. So, you have a magnetic meridian at a location to be given in terms of, supposing I want to find the magnetic meridian in Delhi right now here in the studio. So, I put my freely suspended magnet. This is going to rest in response to the Earth's magnet, and the line joining this is going to be along the line of the magnetic axis of the Earth. So, the plane passing through this is going to contain that axis as well as the axis of this freely suspended magnet. This now becomes the magnetic meridian. We can also be talking about the equator. The geographic equator, as we have seen, is this circle which is along the center of the globe, and if I take a plane perpendicular to the axis of rotation at the center, it would be passing through the geographic equator. Likewise, we can imagine and talk about the magnetic equator as well. These are important and relevant definitions because we are now going to be describing the elements of Earth's magnetic field. There are only 3 elements or 3 requirements to talk about the Earth's magnetic field at a particular location. First one is angle of declination. This angle at a location is the angle between the geographic meridian and the magnetic meridian. If you look at it like this, that if I mark a plane and this plane is showing me the geographic meridian and making an angle with it is a magnetic meridian here like this. This angle is my angle of declination. Why is it relevant? because declination is going to become greater and greater as we go towards the north pole or towards the south pole. At the equator it is minimal. Now, talking about angle of declination, first let us see how we can show it. Supposing I take a section and mark the slice from the center of the globe, and I have a north and a south here, which is my geographic axis, and supposing I also mark on it my magnetic axis, and I talk about the plane containing the two. So, it will be something like this. So, the angle between these two planes, the blue plane showing the magnetic meridian and the yellow plane showing the geographic meridian, this angle is angle of declination. As you can see from here, this value of angle of declination is smaller near the equator, and it becomes larger as we go along higher in latitude. In Delhi, its value is only 0.1 minutes, not even a degree, but as you go closer to the poles, this value becomes higher and higher, 11.3 degrees, which is huge. The next element to be looked at is angle of dip. Now, we are going to be talking about a magnetic needle which is capable of moving about a horizontal axis. That means, it is capable of moving like this. Now, if you talk about a needle which is allowed to do so, you can have random variations, and wherever it will stop you will say, okay, this is another option, this is another option, but that is all irrelevant. What we are going to see is the dipping angle of this needle in the magnetic meridian. So, for that let us first establish using this compass needle here, establish the magnetic meridian, which is this plane, and there is a special apparatus called the dip circle. It looks like this. It has got a needle, and as you can see, this is its axis of rotation. So, it is pivoted along an axis like this, all enclosed in a glass chamber only to keep air off from it. It is marked, there are markings all along here. This would be 0, 0 and this is 90. The beauty of this apparatus is that you can adjust it by moving it along a vertical axis, adjust it so that this frame lies in the magnetic meridian. Now, the needle will stop at a particular location on the surface of the earth, depending upon where it is, depending upon the latitude, depending upon the value of the earth's magnetic field there, and it will rest in the direction in which the magnetic field is. Now, the angle that the horizontal, you consider this horizontal in the magnetic meridian, the angle made by this needle in the magnetic meridian with the horizontal, this is known as angle of dip. If you have understood well, this angle dip is going to vary from place to place. It will be 90 degrees at the magnetic pole, that means whether it is the magnetic south or magnetic north. It will be 0 degrees at the magnetic equator, and for all other positions this will be some other value between 0 and 90. So, at the poles, if I were to take my dip circle, it would rest like this. I can make it do that here, because in the studio it is influenced by Earth's magnetic field in Delhi, and therefore, this cannot be shown that this will become vertical or it will become horizontal. You will have to think about how you can show it as horizontal in the lab experimentally, and it can be done. What do we use this angle of dip for? We can find the value of Earth's magnetic field at a location. How do we do that? We can find the horizontal component by any of the methods using field lines, placing them on a board on a horizontal table, finding a neutral point and calculating the value of horizontal component of Earth's field. Now, what is important is that how do we use the angle of dip and what do we use it for? Finding this value of total intensity, vertical component is here, horizontal component is here, this is my magnetic meridian, this plane, the needle here, this is geographic meridian, the angle between these two is your angle of declination. We are making no use of that for calculation of the total intensity of Earth's field. The angle of dip is important, that is the angle that you can see here, and that will give us the vertical component V to be equal to f cos theta, where theta is the angle of dip, and the horizontal component H would be f sin theta, which will be again established from the angle of dip, or we can say tan theta or tan of dip angle is the ratio of vertical and horizontal components. You can get the value for total intensity I. This value of total intensity on Earth at a particular location, say Delhi, we can take the value is 0.36 Gauss. At other locations it would be different, as you can see, because angle of dip would be different. So, three elements of Earth's magnetic field are angle of declination, angle of dip and horizontal component of Earth's magnetic field. So, let us sum up some facts about horizontal component of Earth's magnetic field. For one thing, it will vary from place to place, angle of dip is varying. Then it is going to be equal to the total intensity of Earth's magnetic field at the equator, angle of dip is equal to 0. So, today you have learnt the three elements of Earth's magnetic field: angle of declination, which was the angle between the magnetic meridian and the geographic meridian. Then you learnt about angle of dip, which was the angle made by a magnetic needle in the magnetic meridian with the horizontal. And you also learnt about the horizontal component of Earth's magnetic field, and these three elements can easily describe all the requirement for knowing how much the Earth's magnetic field is affecting anything that we are doing on the Earth. I am Anuradha Mathur. I have been teaching physics at Modern School Vasant Vihar in New Delhi. We are going to learn about magnetic properties of materials. We are going to classify them under different heads. We are going to see how we do this classification, what is its basis. We have learned that electric currents, moving charges are associated with magnetic field. In an atom, the electrons are moving and the moving electrons form the current. Therefore, every electron in any atom is associated with a magnetic field. If we look at an orbit and an electron, let us say, and let us consider an anti-clockwise direction for it. In this anti-clockwise direction, the magnetic dipole is set up in the direction of the arrow. Its value is given by I into A, where I is the current on account of the electron movement and A is the area of the loop that it makes. Here the loop would mean and be identified by the orbit. Therefore, in a bulk matter, you have a large number of electrons and a large number of atoms to deal with. Therefore, you will have to say that all these magnetic moments are going to be added vectorially, and as such you can describe magnetization for it as the net dipole moment per unit volume. Therefore, all materials are magnetic. How do we classify them further? What happens to them in an external magnetic field? How much of magnetization is changed within them are going to be our governing factor. I have a solenoid over here. This solenoid will generate a magnetic field in its core given by B is equal to mu naught N I, where mu naught is associated with permeability of the core inside. We have nothing here, it is just air. We can take it to be nearly vacuum therefore, and N is the number of turns that I have on the solenoid per unit length. Also the current that I pass through it is my I value. So, the field that is generated here is on account of the current flowing through the solenoid. Within this a magnetic field is generated, and if I were to place different materials in this, I can either increase this field or decrease this field, which would mean that what is the contribution of the material for increase or decrease of the magnetic field inside the solenoid. We can then form a method of describing materials and how they behave in external magnetic field. We need to describe permeability. Permeability is that which shows you how much of magnetic field is allowed to pass through a material. That means, in terms of the magnetic flux, how much of flux is allowed to pass through a magnetic material or any material for that matter. Let us do this small experiment and see how a magnet, this is an external magnet, which I am going to see what is the influence on this magnet by the current passing through this solenoid in the absence of any material inside it. I switch on the current in this solenoid and just hold this bar magnet. The very fact that it is being attracted towards it means that this is getting magnetized. Now, I am going to take this iron rod and insert it inside the solenoid, and you will see the influence on this external magnet. It is getting not only attracted, totally aligned, and it is getting stuck to this particular material. Whether I took the rod in this direction or reversed it, the effect would be the same. The reason for that is that the total magnetization inside this bar has contributed towards the magnetic field of this solenoid. That means, some materials are going to add towards it, the others are going to decrease it. We need to describe another quantity which is called susceptibility. Susceptibility is the measure of how much of magnetization is produced by the external field. So, if I say talk about it as M, then M is equal to xi times H. Xi is how we represent susceptibility, and it tells us how much of magnetization is developed in the material per unit external magnetizing field. H here is Ni, and therefore, M upon H is going to be my value of xi. Its unit will be cancelled, there will be no unit for it. The unit for magnetization is ampere per meter, and so is it for H, ampere per meter, and there would be no unit for our values of susceptibility. Let us see totally in effect how is this net magnetic field that is generated inside the core of this solenoid calculated if I were to add the magnetic field generated due to the current in the coil and due to this additional material that we placed inside it, for which susceptibility may be given as xi. This value can be written as B is equal to mu naught H plus mu naught M, mu naught H is the contribution by the current in the solenoid, and mu naught xi H is going to be that due to the material. So, B is equal to mu naught 1 plus xi H, or mu r is equal to 1 plus xi. What is mu r? Mu r is relative permeability. That means, you compare the permeability of the material to that of vacuum. That means, how much more is the allowance for the flux through a material is governed by the relative permeability. Obviously, permeability and susceptibility should be related, and this is our relationship, mu r is equal to 1 plus xi. Let us find an explanation for all this. How come we have this relationship? How come we can treat materials in terms of the magnetization that is produced inside it? We have what is termed as domain theory. Now, let us describe what a domain is. A domain is nothing but a cluster of atoms within the material for which the dipole moments are in one particular direction. That means, vectorially adding up the contribution of dipole moments created by individual electrons in the sample is going to be in a particular direction. So, in a sample you may have atoms up to 10 raised power of 11, and these are going to be showing a dipole direction in a particular way, and this can then be contributed and seen for the entire material. As per domain theory, the alignment for different domains may be different in a sample, and these may become aligned in a particular direction when placed in an external magnetic field. The response of the material to change the orientation of the dipole moments in different domains for a particular alignment is going to be our reason for classification. We have materials which do not allow this, or in effect change the orientation in a particular way, in a way kind of repel it. That means, the orientation changes, but an effect of repulsion to the external field generates. Such materials are classified as diamagnetic substances. Examples of these are oxygen, aluminum, sodium, platinum, etc. Some of the common materials these are. You can have a situation where the susceptibility and permeability are both positive, which means that the alignment for the dipoles is in the direction of the external field. Whether it is of small value, that means value of susceptibility being slightly positive, and these values are going to make the material paramagnetic. If it is very high, like we had in the case of a iron rod, then we term it as ferromagnetic substances. So, like we had classifications of material on the basis of density, on the basis of its state, etc., we now have a new classification of materials on the basis of material reacting to an external magnetic field, or in turn its magnetic property. So, we have three classifications: diamagnetic, paramagnetic and ferromagnetic substances. Diamagnetic substances which tend to repel the influence of the external field, they have a negative susceptibility, they are going to align perpendicular to the external field, their permeability is very, very low. And if we were to describe paramagnetic substances, they have a positive susceptibility, they have allowance or more permeability for the flux to pass through the material, they can easily be converted into magnets and form a basis for using them in useful ways. You have ferromagnetic materials for which susceptibility is extremely high, permeability is very, very high, and they easily can be magnetized, they can become magnets. So, when we are looking for temporary and permanent magnets, we have to choose materials depending upon what our requirement is. Do you think temperature could change all this for a material? Well, yes. You describe Curie temperature, which is the temperature at which a ferromagnetic substance becomes paramagnetic, or a paramagnetic substance tends to becoming a diamagnetic substance. These temperatures are usually very, very high. For iron, this temperature is about 770 degrees Celsius or 1043 Kelvin. We have learnt a new way of classification of materials. We have been doing that in terms of density, in terms of state, solid, liquids and gases. This time we did it in terms of the magnetic property. That is, what happens to a material when placed in an external magnetic field. That each material has an associated magnetic field inbuilt inside it due to atoms and the electrons that move in them. Every electron in the orbit moves, it has an associated magnetic field, there is an associated dipole moment, there is a net vectorially added dipole moment per atom, and therefore, we can describe the material having domains, and on the basis of all this we have materials that we are classifying as diamagnetic, paramagnetic and ferromagnetic. This is all for making use of materials in different ways for making permanent and temporary magnets.
In the last lecture, we dealt with the force on a current carrying conductor placed in a magnetic field, and we found that this forms the basis of instruments called galvanometers, which detect current. Galvanometers can be converted into ammeters, so that current can be measured. Galvanometers only detect, ammeters measures the current, and galvanometers can also be converted into voltmeters, which measure the voltages or the source voltage that is there in the circuit. In this lecture, we start with magnetism, and the first thing, this I have done many times, this may appear to you to be repetitive, but it needs to be said. You see, we learned that poles can never be isolated. We must have, each magnet has two poles, however small or however large, it has two poles. If we want to find isolated poles, then we can approximate only. We have very long bars, and the ends of these can be considered as isolated poles. Otherwise, isolated poles or monopoles do not exist. And force between the two poles is like the force of gravitation between two masses, or the force of electric attraction between two charges is equal to mu 0 by 4 pi into m 1 m 2 by r squared. It is inversely proportional to r squared. And the Gauss law, again like we did in the previous one or two lectures, is B dot d s is equal to 0, which is a statement of the fact that monopoles do not exist, and which also tells us that the magnetic field lines must form loops. This we have done. So, I am going through this quickly. The magnetic field intensity we can define in the same way as the electric field intensity. We say that if there is a magnet, it creates around itself a field in which, if another magnet or a current or a charge is coming, then it will feel the effect of this field, and the intensity of this field formally can be defined as this. We never get this field, actually we have field due to a dipole all the time. And like other fields, magnetic field also is depicted or pictured through the field lines. magnetic field lines. And you know, you must have done this experiment of drawing the magnetic field lines due to a bar magnet. And you also know that the tangent to a line, whether it is electric field line or magnetic field line, the tangent to such a line gives us the direction of the field. And since the tangent gives the direction of the field, the two lines cannot cross, because then there are two tangents and there will be two directions of the field, which is not possible. At each point the field is unique, it has a certain direction, it does not have two directions, and therefore, the two lines cannot cross. There is a tension along the lines of force. I have told you many times before that the lines of force or the magnetic field lines, they act like springs. If I stretched springs, if I let them go, then the spring contracts. Similarly, the field lines also tend to contract, and they give rise to, because of this effect of contraction along the length, they give rise to the attraction between the two opposite poles. And they also have lateral pressure, that there is a pressure across the lines of force, and this gives rise to the repulsion between similar poles. Now, a short bar magnet acts like a magnetic dipole, and its moment we have seen is the strength of the pole into the distance between the poles. It does not matter whether they are in a straight line or not. Even if the magnet is bent like this, the dipole moment would be the distance between these two poles and the strength of the pole. It does not matter what the shape of the magnet is. The distance between the two poles and the strength of the pole, the product of these two is called the dipole moment of the magnet. And magnetic dipole behaves exactly like an electric dipole, which we have done many times before, and therefore, I just quote the results. The method of finding the expressions is the same. So, I just quote the result and draw parallel between the electric and magnetic dipoles. At a point on an axial line at a distance much larger than this length of the dipole, that is, this is the dipole, then the axial line is this is the axial line that is along the dipole. The field is given by mu 0 by 4 pi into 2 m by r cubed. M, you remember, is the magnetic moment of the dipole. Parallel is drawn with the electric field. The electric field is 1 by 4 pi epsilon 0 into 2 p by r cubed, where p is the dipole moment of the electric dipole. At a point on the equatorial line of it at a distance much larger than the length of the dipole, that is, if this is the dipole, then I am finding the field at a point on a line which is perpendicular to the dipole, then the magnetic field is given by mu 0 by 4 pi into m by r cubed, where m is the magnetic moment, and the corresponding case in the electric field would be E equal to 1 by 4 pi epsilon 0 p by r cubed, where p is the electric dipole moment. Torque on a magnetic dipole, we just saw in the last lecture, is m crossed b, and the parallel is p crossed E in the electric field case. So, the torque on an electric dipole in an electric field is p cross E. The torque on a magnetic dipole in a magnetic field is m cross b, and the work done or the potential energy of a dipole in a uniform magnetic field is minus m dot b. So, you see it is energy, therefore, it cannot be vector, it must be dot product. So, minus m dot b, and the parallel case is minus p dot E in the electric case. Time period of oscillations of a dipole in a uniform field, you see, if I have a uniform magnetic field and shift it slightly, then it starts oscillating. Similarly, with the electric field, and you can easily show that these oscillations are simple harmonic. Remember, what is a simple harmonic oscillation? In which the acceleration is proportional to the displacement and is in the opposite direction. So, if you use that rule, then you can show that the time period of oscillation of a dipole in a uniform magnetic field is 2 pi square root of 1 by m times b, and in the case of electric dipole it is 2 pi 1 by m times b, this is 1 by p times E. Now, let us take the case of atomic physics, that an atom has a nucleus and then large number of electrons going around this nucleus, and these electrons, they are charges, and since they are moving they constitute currents. And we have seen that if you take a charge and if it takes time t to move around, then it is equivalent to a current E by t, and t is nothing but omega by 2 pi. So, the equivalent current is E omega by 2 pi, where omega is the angular frequency of the charge, and the magnetic moment of this current or this electron moving around the nucleus is the the current times area. Remember that. So, it is E omega by 2 pi, which is the current, times the area, which is pi r squared. So, it is E omega r squared by 2. That is the magnetic moment of the electron moving round the nucleus with frequency omega and of radius r. Now, according to Bohr theory, the angular momentum in the nth orbit of a charged particle is, if I is the moment of inertia, is I omega, which is m r squared omega, which is equal to n h by 2 pi. You remember, this h is Planck's constant. Bohr said that you cannot have any angular momentum, the angular momentum must be quantized, they must be 1, 2, 3. So, n can be 1, so it is n h by 2 pi, 2 h by 2 pi, and like that. That is the angular momentum of an electron moving around the nucleus according to the Bohr theory. And if I substitute omega in the expression for the magnetic moment of the electron, then this is the expression for the magnetic moment. So, I am going to substitute omega from here, and I get m equal to n E h by 4 pi m. I have taken n outside because n can be 1, 2, 3 depending upon the orbit of the electron. So, in the first orbit n equal to 1, this m is E h by 4 pi m. I can substitute the values, and this m turns out to be 9.27 10 to the power minus 24 a m square. You know the units, current into area. So, a m square. This is called Bohr magneton. This is the magnetic moment of the first orbit, and we can measure the magnetic moments of other orbits in terms of this Bohr magneton. Now, Earth's magnetic field, we all know that Earth has a magnetic field. How do we know? We suspend a magnet, and this magnet always settles in a certain direction, which is north south direction. Therefore, this indicates that Earth has a magnet, or Earth behaves like a magnetic field. But where does this magnetic field come from? The origin of the Earth's magnetic field, although so important to us, is not very well understood. But scientists know that there are 3 things that must be there for a magnetic field to develop, for a magnetic field to become considerable. And what are those 3 things? A seed magnetic field, that means a very weak magnetic field must be there to begin with. This weak field can be amplified, but we can't start from 0 field. So, we need a seed field in the earth and a source of energy for the production or amplification of this seed field, and the motion of an electrically conducting fluid. Motion of an electrically conducting fluid is like a current. So, we need a current to amplify the magnetic field. You know, current has a magnetic field, therefore, it can in some way amplify the present or the existing magnetic field. Conducting fluid is equivalent to an electric current. It interacts with the seed field and sets up complex processes which amplify this field and maintains this amplified field, and these complex processes are not yet fully understood. The evidence of the presence of a seed field comes from the fact that all cosmic bodies, maybe planet, maybe star, maybe a galaxy, maybe anything, all bodies, all celestial bodies, all cosmic bodies have a magnetic field, whether weak or strong, that is a different matter, but they must have a magnetic field. Therefore, the earth must have a seed field to begin with. The energy for the production of the field, you see, magnetic field, B is a magnetic field. If we are going to increase it, then the magnetic energy will increase. So, energy has to come from somewhere, and what is that somewhere? The energy can come from the rotation of the earth or the convection set up by the heavy matter going down towards the center of the earth and lighter matter coming up. So, this convection or the rotation of the earth can contribute energy if required. Where does the motion of the conducting fluid come? Remember that in the core of the earth the temperature is very high and iron is there in a liquid form, and since it is in a liquid form, it rotates with the earth, and therefore, we have a rotating conducting fluid which is equivalent to a current, and this is the current that sets up processes which amplify the existing field or the seed field. Details of this dynamo process, dynamo is a device which produces the electricity or in this case magnetism, and this dynamo process we know it exists, but we do not know its details. What we do know is that the magnetic field must be produced and maintained continuously. You see, there you may think that the magnetic field was produced once and that is it. That is not possible, because if once produced, then over time, over a very long time, the field strength reduces, comes down to lower values, and therefore, we cannot say that field was produced once and that is it. It must be produced continuously, so that the field is maintained at a certain value. Produced once, it can come down and that will be the end of it. So, we want that there should be a continuous process which amplifies the field that is present, so that the field of the earth is not lost. And all these, for details of all these interesting things, you can visit this source www.geomag.bgs.ac uk/education/reversals. There is a lot of material on this website. The magnetic field of the earth is something like this. The earth behaves as if a very strong magnet, bar magnet, is placed inside it. Of course, there is no bar magnet, but the lines of force or the magnetic field lines that we draw, they indicate that the field is dipolar, mainly dipolar. That means that as if not actually, as if a magnet is present. So, I have shown this magnet, but there is no such magnet. I have just shown it to show you the lines of the field lines, and this green line is the axis of the earth, rotation axis of the earth, and the red line is the magnetic axis, that is the line joining the magnetic north and magnetic south. In this lecture, we saw a very important and very interesting, to me at least, topic of Earth's magnetic field, how it varies and how it could reverse, and it has reversed in the past. Several times, in fact, it has reversed in the past. In next time, we continue with magnetism in the next lecture.
Hello viewers, today we are going to start our series on continuity and differentiability, and the very first concept that we are going to talk about is of continuous functions. The concept of continuous functions is very close to the literal meaning of the word continuous. A process or an event is said to be continuous if it continues without stopping, and that is exactly what we are going to look at through graphs of functions first. Here we have graphs of two functions which seems to be very smooth, running without a break or a gap, and that is exactly what we are looking for as we discuss the concept of continuous functions. What about these two graphs here? If you have to trace them with a pencil or a pen, would you be able to do that without lifting your pencil? Surely not. What about this one? This also seems to have a little hole at x is equal to 1. Do you see that small hole at x equal to 1 marked by a small circle in black? Even if you do not have to lift your pencil too high, it still brings a break in the graph. Such functions would be discontinuous functions. Let us examine these functions a little closely to see what creates this discontinuity. Here we have a function, one of the earlier graphs. Function here is defined as when x is less than 1, f x is equal to 1. When x is greater than or equal to 1, it takes a value 2. Now, what this definition of the function do is, it gives two different heights to the function for x less than 1 and x greater than 1, and that is what causes this gap between the two graphs, and therefore results in a discontinuity. Whereas in this one, the function is x square minus x by x minus 1, clearly not defined at x is equal to 1. And so, x is equal to 1 is not in the domain of the function, and therefore, you have to leave a little mark, a little gap at x is equal to 1 when you draw the graph of this function, and therefore, again discontinuity because the function is not defined at x is equal to 1. Whereas, as compared to the previous graph, from both the sides of 1, it is going towards the same height, right. What about the third one here? Again a very peculiar situation. At x is equal to 1, the graph is definitely not defined. The function is not defined. 1 does not belong to the domain. What are the other two things that you can observe as you see this graph? When x takes values less than 1, do you see the graph, pink graph on this side, plunging right towards the negative infinity, whereas on the greater side of 1, very close to 1, as x takes values very close to 1, but more than 1, the graph seems to be going up towards positive infinity, again giving rise to a break in the graph. So, what we have observed right now with these three graphs are the various reasons for which the function becomes a discontinuous function. So, how would one define a continuous function at a particular point? What you need to understand is that the function will not show such behavior if at a particular point the function takes the same height from the two sides of the point, right. And most importantly, the function must be defined at that point, and the actual value, that is the attained value of the function at that point, equals what we call as the intended height of the function. So, the function converges towards the same height and the height exists at that particular point, then there will be no reason for the graph to have a break or a gap. And that is what our concept of limits also said something. It said something about converging towards the same height, but the height need not exist, remember. So, let us put it all together and give you the definition of continuous function at a certain point. The definition says, suppose f is a real function on a subset of the real numbers, and let C be a point in the domain of f, then f is continuous at C if the limit of f x as x tends to c equals the value of the function at x is equal to c. Isn't that what I just described by saying that the intended height must be equal to the attained height? The function must converge to the same point, the same height from the two sides of x is equal to c, and there should be an f of c as well there. So, that is what we are going to now examine algebraically given a function. You know very well that graphs are not so easy to define and draw without a particular software. You are very restricted in terms of defining and plotting those graphs of functions which you will now examine algebraically. So, we would expect you to have a very good understanding of the algebraic method of finding or discussing the continuity of a function at a particular point. So, let us begin with our very first problem, and the question says examine the continuity of the function f at x is equal to 0, where f of x is defined as x minus mod x by x when x is not equal to 0 and takes the value 2 when x is equal to 0. Now, every time you see a function which involves modulus, absolute value function, the very first thing one must do is restate, rewrite, define it again, keeping in mind that the behavior of mod x depends on whether x is greater than 0 or x is less than 0. So, keeping that in mind, let us redefine our function, and we have the function rewritten for x greater than 0, taking the value 0 because mod x is x, simplify and you get f x is equal to 0. When x is less than 0, mod x takes the value minus of x, and therefore, it all simplifies to 2. At x is equal to 0, the function takes the value 2. So, we are interested in showing that the left hand limit is equal to, or in fact discussing whether the left hand limit is equal to or right hand limit or not. Left hand limit at x is equal to 0 is given as limit of f x as x tends to 0 from its lesser side. That is denoted by 0 with a little negative marked as superscript there. What is this going to be same as? Limit of 2, because when x is less than 0, f x is 2, and limit of 2 no matter where x is going remains 2. Similarly, the right hand limit is limit of f x as x approaches 0 from its greater side. What would that be same as? When x is greater than 0, f x is 0. So, it is limit of 0, which remains 0 as x approaches 0. And therefore, obviously, the left hand limit is not equal to right hand limit, but what about its comparison with the value of the function? Well, yes, the left hand limit does equal the value of the function, but not equal to right hand limit. That would still give rise to a discontinuity at x is equal to 0. I hope that made sense to you. Let us take another problem, slightly more complex, more of discussion to be done here. The problem asks for finding the value of an unknown a such that this function, which is defined differently for x less than 0 and greater than 0 and at x equal to 0, such that the function becomes continuous at x equal to 0. Now, this is one of the problems which I picked up simply because it will brush up lot of techniques of limits for you. So, get ready. For x less than 0, it is a trigonometric function, right? Greater than 0, you have irrational factors. And what do we do when you see an expression like that in terms of evaluation of limits? We use rationalization. So, we are going to bring up both the methods as we go further with the solution. Very first thing, f of 0 is a, that is very clear, defined, let us put that at rest. Left hand limit is limit of f x as x approaches 0 from its lesser side. That is same as replacing f x by its definition when x is less than 0. We use the basic trigonometric identity 1 minus cos 4 x to be same as 2 sin squared 2 x, and that rewritten, redefined so that you can use the limit sine theta by theta as theta tends to 0 to be 1 becomes same as just 8. What about the right hand limit? Again, as we take x approaching 0 from its greater side, f x gets replaced by the function root x by square root of 16 plus square root of x minus 4. And as we said earlier, we use rationalization. So, if I multiply and divide by the conjugate of the denominator, I get simplification to a large extent, and you can see how nicely it just simplifies to root of 16 plus root x plus 4. And as x tends to 0, what would this be? Nothing but root 16 plus 4, which is 8. And so, the left and right hand limit both are same as 8. Value of the function was also given as a. Limit exists equals 8, and therefore, for continuity the left hand limit, right hand limit and the value of the function must be equal. Does not that give us the value of a as 8? So, a question which brought up lot of interesting techniques that you may have forgotten, because this is what you learned in grade 11, suggests that you do need to brush up the concept of limits before you try your hands on continuity of the function. At the same time, there are number of small but significant results which we need to be ready with. So, get down to writing them down and keep them in mind as we progress further down with this topic in our subsequent lessons. One of the results suggests that if f and g be two real functions continuous at a real number c, then their sum, difference, product and the quotient with the condition that g of c should not be 0, they all are continuous at x is equal to c. We also have an understanding and a result about the composition of two continuous functions. So, if f and g are two real valued functions such that the composition f of g is defined at c, g is continuous at c, f is continuous at g of c, then we say that f of g is continuous at c. Another very important understanding is what do we mean by continuity over the entire domain, because our earlier definition was about continuity at a particular point. We say that a real function f is said to be continuous if it is continuous at every point of the domain of f. We also have a definition for a function to be continuous over its entire domain. A function will be continuous if it is continuous at every point of its domain. This and our next list of results which tell us what are those standard functions which are always continuous is going to help you build up on the further concepts that you are going to come across in this chapter. We have results which suggest that every polynomial function is continuous, every rational function is continuous, sine and cosine functions are continuous, absolute, logarithmic and exponential functions are continuous. These are results which are not too difficult to prove, but for the time being we are not covering their proofs, but we will be using and referring to these results in our future lessons. I hope today's lesson has brought in some clarity on this abstract concept of continuous functions. We will continue with more on continuity and differentiability in our subsequent lessons. Thank you. Hello viewers, welcome to our second lesson in the series on continuity and differentiability. In our first lesson, we talked about the continuous functions. Today, we will discuss differentiability of a function. You were introduced to the concept of derivatives in grade 11. Do you remember how we define derivative of a function at a particular point? Let us refresh your memory. The definition says that if f is a real function and c is a point in its domain, then the derivative of f at c is defined to be the limit of the quotient f x minus f of c and x minus c, if this limit exists. Now, the whole discussion of today is on this condition, this limit exists. The limit may not exist. When does the limit exist? When do we say that f dash c is defined? You remember very well that the limit of any function as x approaches c depends on two quantities called as the left hand limit and the right hand limit. So, this limit, that is limit of f x minus f of c upon x minus c, again depends whether as x tends to c from its lesser or greater side converge to the same value or not. And that is what brings up the definition of left hand and right hand derivatives. What is left hand and right hand derivative? Left hand derivative is defined as limit of f of x minus f of c upon x minus c as x takes values lesser than c, but very close to c. And the right hand derivative, well, you guessed it right, it should be limit of f x minus f of c by x minus c as x takes values closer to c but greater than c, indicated as c positive. And we say that a function is differentiable at x is equal to c if these two limits, that is the left and the right hand derivative, are finite and equal. That is what the concept of differentiability of a function at a particular point requires. So, we will now take few problems where we will examine these limits and discuss whether the function is differentiable at a particular point or not. A function f is said to be differentiable in an interval a b if it is differentiable at every point of a b. So, once we know how to examine the differentiability at a point, we also have an understanding of what it means by a function differentiable over a certain interval. There are few other results which will help us as we go further down in our lesson. And the very first theorem says, if a function f is differentiable at a point c, then f is also continuous at that point. A very significant result, and the proof is not too difficult. I will suggest that you do try the proof. Today, we will only concentrate on the problems. We also have a result coming as a corollary which says that every differentiable function is continuous. What about the converse? The converse is not true. One of the examples that you can easily see as we go further with testing the derivability at a point will be of the modulus function. You know that it is a V-shaped graph, remember? So, it is continuous, and subsequent part of the lesson will teach you that it is not differentiable at x is equal to 0. So, remember these results and refer to them as and where the need arises. Let us take a problem to discuss the differentiability of a function at a particular point. The problem states, examine the differentiability of the following function f x at x is equal to 2, and how is the function defined? For x less than 2, it takes the value x minus 1. For x greater than equal to 2, it takes the value 2x minus 3. before we get down to finding the left and the right hand derivative, let us take a look at its graph. This is the graph of the function that was just defined. Examine and see that it has two paths. For x greater than 2 and less than 2, the definition is changing. There is no gap in the graph. So, it is a very much a continuous function. But do you notice that at x is equal to 2, there is a sharp corner being formed. Any function which has a sharp corner in its curve is not differentiable at that point. Why? Because you cannot define a tangent at those points, and therefore, the concept of differentiability which was related to the understanding of the tangent slope suggests that if a curve has a sharp corner, or of course, if it is breaking, the function will not be differentiable at these points. But this is not enough, and you cannot plot graph of each of these functions. So, let us get down to finding the left and the right hand derivative. The left hand and the right hand derivative come from the definition given earlier. Right hand derivative is limit of f x minus f of c upon x minus c as x takes values greater than c. That gets replaced at x equal to 2 by f x minus f of 2 by x minus 2 as x approaches 2 from its greater side. The definition of the function suggests that f x is 2x minus 3 when x is greater than 2. So, replace f x by 2x minus 3. Simplify and also note that f of 2, that is the value of the function, is coming again by the same relation because 2 was included in this branch. F of 2 turns out to be 1. This simplifies to be nothing but limit of just the constant 2 and therefore 2. So, right hand derivative is 2. What about the left hand derivative? Again, it is limit of f x minus f of c by x minus c as x takes values less than c, but close to c. At 2, again f x less than 2 takes the value x minus 1, f of 2 remains the same 1. That is nothing but all just simply 1. So, what do you observe? Left hand limit, that is the left hand derivative, is not equal to right hand derivative at x equal to 2. So, what do we say? F is not differentiable at x is equal to 2. Let us take another problem, a little more elaborate. It says for what values of a and b is this function derivable at x is equal to 1. Here we need two unknown values, that is the value of a and b, but we have a condition only about derivability. I think you have all gone through the process where you have understood that to find two unknowns, we must know at least two conditions. So, what is the second thing you know about this function? A function will be derivable at x is equal to 1 if it is continuous at x is equal to 1. So, that is an unsaid condition in the question which you need to start with. Let us begin and see what we get as we look at continuity at x is equal to 1. Left hand limit is limit of f x as x takes values less than 1, which is same as limit of x square by the definition, and therefore, the left hand limit is simply 1. The right hand limit is limit of f x as x takes values greater than 1. Replacing f x with 2a x plus b, we get 2a plus b, and therefore, the left hand limit equal to right hand limit will ensure that the function is continuous at x is equal to 1. So, the left hand limit is 1, right hand limit is 2a plus b. What about f of 1? The value of the function is 1 square, which is simply 1. So, the function will be continuous at x is equal to 1 if the left hand limit equals right hand limit equals the value of the function. That gives rise to the condition 2a plus b equal to 1. Hold on to that and let us begin the conditions on derivability. F is derivable at x is equal to 1 if the left hand derivative equals right hand derivative. The left hand derivative by definition is limit f x minus f of c by x minus c as x takes values closer to c less than c. What do I get here then? At 1 we replace f x by its value when x is less than 1. At 1 it takes the value 1. So, the limit becomes limit of x square minus 1 by x minus 1, which is nothing but limit of x plus 1. As x approaches 1, that is same as 2. So, the left hand derivative at x equal to 1 takes the value 2. What about the right hand derivative? Right hand derivative again can be processed in the same manner, making sure that when you replace f x, you follow the definition which said that f x is 2ax plus b when x is greater than 1. Now, we need to figure out how to find this limit, and that is where we use the idea that 2a plus b is equal to 1, and therefore, the limit simplifies to be just the limit of 2a, and that is nothing but just the constant 2a. So, we have the left hand derivative as 2, right hand derivative as 2a. Therefore, the function will be derivable at x is equal to 1 if 2a is equal to 2, that is a is equal to 1. Once I have the value of a, we are surely close to finding the value of b, since 2 of a plus b is equal to 1. Does not that give you b equal to minus 1? And that is exactly what the question asks for. The function will be derivable at x is equal to 1 if a is 2 and b is minus 1. I hope with these questions you become more confident of discussing the differentiability of a function at a given point. Do not forget that both the concept of continuous functions and differentiable functions depend heavily on the concept of limits. So, do brush up some of the basic techniques of evaluation of limits, and then nothing can stop you from attempting any of these questions on your own with confidence. See you in our next lesson next time. Thank you. Hello viewers, today we are going to discuss the techniques of differentiation, and our very first very important rule, that is the chain rule, is our focus. The chain rule is a rule of finding derivative of functions which are composition of two or more functions. Let us take a short visit back to the understanding and the idea of composition of functions before we get down to the chain rule. Composition of functions can be very well understood if we look at a pair of function machines. Here we have a function machine G whose input is a ball, a sphere, and the output results in a cube. This output, when dumped into the function f, results in an output of a faceted ball. Together, they can be expressed as a big function machine where a ball is dropped in and it results in an output of a faceted ball. In mathematical terms, what does that mean? If I take x to be the input of G, it results in u as an output of G, same as G of x. This goes in the function machine f and results in an output f of u. Together, as I look at this as the composition, it would mean same as saying that x is the input and what is the output? Represented as f of g of x. That is exactly what we mean by composition of two functions. The chain rule is a rule of finding the derivatives of composition of two or more functions. Here is the rule without proof for you to follow and understand. If f is a composition of two differentiable functions f and g, that is f of x is same as, note the difference, that is a capital F is same as f of g of x, then capital F is differentiable and its derivative is product of the derivative of g and the derivative of f at g of x. So, it is same as f dash of g x into g dash x. Sounds confusing. Let us take another look at the same definition restated. Suppose capital F is the composition of small f and g, and let us call u to be g of x. Try to relate it to the picture that you had seen just a minute earlier. Then f of x is f of u, right? So, the chain rule says that derivative of f with respect to x is same as derivative of small f with respect to u, because now small f is a function of u. The output of g goes into f into the derivative of u with respect to x. So, there is a chain of continuation, there is a chain that you can see going from f to u, then u to x. So, you differentiate small f with respect to u, multiply it with the derivative of u with respect to x. That is what the chain rule of differentiation says. This gets extended to 3 or more functions, and we have a rule which says that if capital F is a function which is composed of f, g and h in that order, and if v is g of u, where u is h of x. So, you kind of come through the layers and you say h of x is u, and then the outer layer v, which will be g of u, such that the function capital F becomes f of v. Then what will be the derivative of capital F with respect to x? As I said, use chain rule, extend chain rule. What does it give us? Derivative of f with respect to v into the derivative of v with respect to u, because v is a function of u, into derivative of u with respect to x. This chain can be continued depending on the number of functions that are involved in the composition. Now, there is nothing that can replace actual application of the chain rule to get the hang of this rule. So, let us get down to applying this to our very first function. The question says differentiate sine of root x with respect to x. Notice that this is definitely a composition of two functions, sine function and the square root function. So, to find the derivative, we definitely need the chain rule. So, our function, let us call it capital F, is sine of root x, and let us take the inner function, inner as in this case the second function root x to be u. Then f of x is nothing but sine of u, and therefore, by chain rule df by dx is same as the derivative of f with respect to u into the derivative of u with respect to x. that is same as cos of u, because derivative of sin u with respect to u is cos of u, into derivative of u, which is derivative of root x, is same as 1 by 2 root x. Replace u with root x and your answer is ready. Let us take a question where we have a little more complex composition. Here the question is, if y is equal to x plus root of x square plus a squared raised to the power n, show that dy by dx is n times y by under root of x squared plus a square. If you see the function y here, do you observe that there is composition involved? And not only composition, there is a sum of two functions as well, that is x plus under root of x square plus a square. This sum is raised to the power n. So, there is definitely more layers involved in this function. Let us see what we will do as we start the derivative. Let us take the inner function, that is the function which is the base, to be u. So, let u be x plus root of x square plus a square. So, clearly y is equal to u to the power n, and therefore, by chain rule the derivative of y can be read as derivative of y with respect to u into derivative of u with respect to x. Now, derivative of y with respect to u is nothing but n u to the power n minus 1. It is the derivative of u that needs more work. So, again going back to our function u, which is of course x plus root x square plus a square, it all simplifies, that is the derivative of y with respect to u simplifies to be this expression. Let us focus on u. U is x plus root of x square plus a square. It is just not sum of two functions. The second part of this function is again composition. So, let us just take that to be z. So, if z is root of x square plus a square, then the base function, that is x square plus a square, can be taken as w, and therefore, z becomes root of w. Are we ready then to find what dz by dx is going to be? So, dz by dx, that is the derivative of z with respect to x, is nothing but derivative of z with respect to w into derivative of w with respect to x, and that is nothing but 1 by 2 root w into 2x. Put back the value of w and you have the derivative of z with respect to x. So, our u, which was nothing but x plus z, has the derivative ready as 1 plus x by root x square plus a square, which may be again rewritten. But that is not the end of the problem. We go back to finding what dy by dx was. So, I already have dy by du and now I have du by dx. Using the chain rule, I have dy by dx written as the product of these two expressions. Notice that the two expressions which are being multiplied have something common. So, if you use the rule that if the base is same, powers get added, the expression does simplify to be nothing but n y by root x square plus a square, but because y was x plus root of x square plus a square whole to the power n. So, a more complex, more of a u, v, w and a z coming in sounds confusing and time taking as well. Will this be a practical approach for all the other problems that you come across? Well, may not. So, we need to reinvent our strategy and then use the chain rule. Let us take a problem and see if I can explain to you how to cut short this assumption of u, v, w. So, we have a question which says find derivative of cos of sine of root of a x plus b. Do you see how many layers are present here? how many functions are composed? First x change to ax plus b, then the square root function comes in, then the sine function comes in, and then the cosine. So, obviously, it is very well a case of chain rule. Let us see what we do if I start with y as cos of sine of root of ax plus b. Starting with the outer layer, that is of the cosine function, the derivative can be written as minus sine of root of ax plus b into derivative of sine of root of ax plus b. So, if you keep the reference of u as we did earlier, if sine of root of ax plus b was u, then you would have multiplied with the derivative of u with respect to x. So, we are going to cut short, we are not going to bring u and v in this method. Now, what is the next layer? Sine function. So, we differentiate the sine function with respect to root of ax plus b, and we get cos of root of ax plus b multiplied with the previous minus sine of sine root ax plus b into the derivative of the next function, that is root of ax plus b, which leads us to the next layer, which is square root. So, the square root derivative would give us 1 by 2 root ax plus b. Inner function is a simpler one, ax plus b, but not an insignificant. If you miss multiplying by a, the derivative is incorrect. And therefore, we have differentiated a function which was composition of 4 functions without bringing this u v assumption. One more question to firm it up for you. Find derivative of cos of x cube into sine square of x to the power 5 with respect to x. What you need to observe in this case is that there is a product involved in the function. So, chain rule is what we are discussing, but we can't neglect the presence of product and therefore, product rule. Recall this rule which we are going to use just now. Starting with our function called as y, dy by dx by product rule gives us sine square x to the power 5 as it is, derivative of cos x cube in plus cos of x cube into derivative of sine square x to the power 5. Now comes the use of chain rule the moment I differentiate cos of x cube. Starting with the outer layer, that is cos, I get the derivative as minus sine of x cube into derivative of x cube. Let us also take a look at the next term also before we complete the first term derivative. Here sine square x to the power 5, the outermost layer is of the square function. So, differentiating I would get 2 times sine of x to the power 5 into the base, the derivative of the base, that is derivative of sine of x to the power 5. Completing the differentiation, we get sine square of x to the power 5 into negative sine of x cube into derivative of x cube giving us 3x square. The second term, you need to just watch out for derivative of sine of x to the power 5, that is nothing but cos x to the power 5 into 5 x to the power 4, again applying the chain rule. What is left is now just a bit of simplification. If something simplifies, cancels, good, otherwise you do end up with a long expression like this as your final answer. I hope students, today's lesson has brought in a lot of clarity as far as the chain rule is concerned. Chain rule is one of the basic rules that will continue to be in use as we explore other techniques of differentiation in our future lessons. See you till then. Hello viewers, today we are going to discuss 2 special methods of finding the derivatives of implicit functions and also the inverse trigonometric functions. What exactly do we mean by implicit functions? So far we have been using functions of the form y equal to f of x, where we had y is equal to sine square 2x plus 1, or y equal to x cube plus 2x minus 1, or y is equal to under root 1 minus cos x by 1 plus cos x, and you could find their derivatives with the appropriate rule applied. Such functions where y is clearly expressed as a function of x are called the explicit functions of x. What happens in these cases? Can you solve y in terms of x? Can you express y as a function clearly written in terms of x? Perhaps as you look at each one of them, you will be able to say no. Such functions where there is a dependence of y on x, but y cannot be expressed explicitly in terms of x, we say that y is an implicit function of x. And today we are here to discuss the differentiation of implicit functions. How do I find dy by dx if I have an implicit function? In this case, the relation is sine square x plus cos square y is equal to 1. So, task is the same. I have to find the rate of change, that is the instantaneous rate of change of y with respect to x, but I cannot express y in language of x directly. What do we do? Let us demonstrate. Differentiate the relation with respect to x, we get derivative of sine square x plus derivative of cos square y equal to derivative of 1. So, we are differentiating both sides of the given expression. Derivative of sine square x is not a problem, but note that cos square of y is present, not x. So, this is where you have to watch out. Using the chain rule, I get the derivative of sine square x as 2 sin x cos x. We are interested now in understanding what would be the derivative of cos square y would be. Again, it is a composition. Outermost function is the square function, then cosine function, and then another function, that is y, which is a function of x present. Therefore, applying the chain rule, I get the derivative as 2 cos of y into the derivative of cos of y, and the right hand side of course is 0, because derivative of a constant is always 0. Further, this becomes same as 2 sin x cos x as it was plus 2 cos y, and now the derivative of cos y using chain rule is minus sine of y into the derivative of y with respect to x. From here, we will just now separate out what dy by dx is. Rearranging, you get dy by dx as sin x cos x upon sin y into cos y. So, chain rule actually plays a significant role in finding the derivatives of implicit functions. Let us consider one more problem and see if there are other things that you need to be careful with. We have the question which says find dy by dx if sine of x y, the product x y plus x by y is equal to x square minus y. Again, differentiating the relationship with respect to x, we get derivative of sine of x y plus derivative of x by y is equal to derivative of x square minus y. The first term, that is sine f x into y, gives us cos x y into derivative of x y, chain rule again, plus what happened here? What I have used is what you see, I read it as x by y. So, there is a clear presence of quotient rule. Right hand side is just 2x minus dy by dx. Work is still not over, because I still have to finish the first term. again applying the derivative of x y with the help of product rule, I get cos of x y into y plus x dy by dx. The other terms remain the same. Our job was to find dy by dx. So, what you really need to do is to rearrange, rewrite this expression and separate out dy by dx, which will give rise to the final answer written here for you. I will leave the little bit of simplification in between for you to follow up with. So, we have the derivative of implicit functions evaluated using the chain rule. Wherever product and quotient rule present, they play a role. Let us continue with understanding how this and other facts that we have learned so far help us to find the derivatives of inverse trigonometric functions. Since we have a limitation of time, I am not going to discuss the proofs of these results, but these results are going to play a very important role in this discussion, and that is nothing but list of these results or formulas, as you may call them, which suggests that the derivative of sin inverse x is 1 by root 1 minus x square, and yes, there is a condition present on x for this derivative to be well defined. So, those branches, the conditions on x are stated along with. You definitely need to memorize these results, there are no alternatives for it, but the best would be if you sit and work out the proof using implicit differentiation only. Start with y equal to sin inverse x and see what x is, and then work out the proof from there. We will focus on the applications. So, if I have to find the derivative of y, where y is cos inverse of root x with respect to x, what would one do? Again observe composition, 3 layers, no rather 2 layers. I have inverse, cos inverse and the square root function present here. Let us see what would happen if I have to find its derivative using chain rule. Do you think I can write directly as minus 1 by root 1 minus x into derivative of root x? What happened in between? Derivative of cos inverse root x with respect to root x by their formula would be minus 1 by root of 1 minus root x whole square. Isn't that so? That simplifies to be minus 1 by under root 1 minus x. And what is the derivative of root x? Nothing but 1 by 2 root x. That gives you the derivative of y with respect to x as minus 1 by 2 root x into root of 1 minus x. Let us take another question. Find dy by dx if y is equal to cot inverse of root 1 plus sin x plus root 1 minus sin x by root of 1 plus sin x minus root of 1 minus sin x, where x is between 0 and pi by 2. Now, one of the things that you must possibly realize as we go through this statement is that this is a very familiar function. Where did you see that? Remember, we worked on these functions in inverse trigonometric functions chapter and learned how to simplify them, how to write them in their simplest form, and in fact that is what is going to take away the major part of our problem. Derivative would only be calculated once this function is simplified. Let us get down to doing that. Start with y, which is cot inverse root 1 plus sin x plus root 1 minus sin x upon root 1 plus sin x minus root of 1 minus sin x. What can we do? I can write that sin x as cos pi by 2 minus x all across. Why would one do that? Simply because 1 plus cos theta is 2 cos squared theta by 2 and 1 minus cos theta is 2 sin square theta by 2. Therefore, 1 plus cos pi by 2 minus x simplifies to 2 cos square pi by 4 minus x by 2, and 1 minus cos x simplifies to be 2 sin square pi by 4 minus x by 2. What is this going to be same as? This is same as writing cot inverse of absolute value of cos pi by 4 minus x by 2 plus sin pi by 4 minus x by 2, and in the denominator the same expression with a negative sign in between. Now, why do we have modulus here? Because square root of a square depends on what a is. Is it going to be positive a or negative a? Depends on a in sense, if a is a positive quantity, then root of a square is going to be a. If a is negative, then root of a square is negative a. So, what do we know about cos pi by 4 minus x by 2 and sin pi by 4 minus x by 2? Are they positive or negative quantities? Remember, there was a condition on x. X is strictly between 0 and pi by 2. So, x by 2 is strictly between 0 and pi by 4. Do you think then we can say that cos and sin of pi by 4 minus x by 2 are both positive quantities, and therefore, y simplifies to be cos pi by 4 minus x by 2 plus sin pi by 4 minus x by 2 divided by cos pi by 4 minus x by 2 minus sin pi by 4 minus x by 2. Now, this is an expression which we have worked with a number of times and know that this can be rewritten as cot inverse 1 plus tan pi by 4 minus x by 2 upon 1 minus tan pi by 4 minus x by 2. In case you have forgotten, what we do is divide numerator and denominator by cos pi by 4 minus x by 2. This leads us to nothing but cot inverse of tan of pi by 4 plus pi by 4 minus x by 2, a very familiar expression. This results in nothing but cot inverse of tan of pi by 2 minus x by 2 leads to cot of x by 2. And see, our y is just nothing but x by 2. So, the derivative of y with respect to x is simply half. So, the task was to find the derivative, and that took not just more than maybe a second to do, but without the simplification it would not have been so convenient to find the derivative. In fact, it is mandatory that you first simplify the expression and then find the derivative. And so, in order to differentiate inverse trigonometric functions, you must perfect the inverse trigonometric functions chapter, and specifically the part where we discuss how to simplify a given expression before you start with the derivatives. Best of luck, work hard, and I will see you next time.
In the last lecture, we were discussing gravity. We found that if a particle is launched from the surface of the earth with a velocity of 11.2 kilometers per second, it will escape the gravitational field of the earth. However, artificial satellites are never launched with this velocity. They are launched with velocities much less than 11.2 kilometers per second, so that they remain in the field of the earth and they orbit the earth and they are bound to the earth. Today, we are starting with the properties of liquids, and the first property that we take is surface tension. You may be knowing that there are two kinds of forces between molecules of a substance. If the molecules are of different kind, then the force of attraction between them is called adhesive force. If the molecules are of the same kind, then the force of attraction between them is called cohesive force. It is the cohesive force which keeps the molecules of liquid, let us say water, bound to one another, so that the whole thing is in equilibrium. You must have seen this phenomenon. There is a beaker containing water and a bottom is slightly wet and it is placed on a plane surface, and the beaker is stuck to the plane surface. You need some effort to lift it, and if you are not careful, the beaker can fall and can break. What is responsible for this kind of behavior? Adhesive forces between water and glass, they are responsible for this kind of phenomenon, and you must be careful if something like this happens. You must have seen this also. If you take two glass plates with a very thin layer of water between them and you join them, then they are stuck to each other. In fact, they are stuck so rigidly that you require a lot of force to separate them. What is responsible for this? Again, adhesive forces between the molecules of water and the molecules of glass. They are responsible for this phenomenon. Now, let us see the following. Suppose we have a liquid and this is kept in a glass vessel or some vessel. What happens? You see, inside the liquid, this is a molecule inside the liquid, and you see that it is interacting with all its neighbors, and the net force on this molecule, blue color, is 0. So, that this molecule is in equilibrium, and this is true of all other molecules. But when you consider a molecule on the surface, then this molecule experiences forces from below and from the sides, from the molecules on the surface. But from the top, where there is air, this force is much weaker, so that this molecule experiences a force downwards, and that is true of all the molecules on the surface. See here, and if the molecules on the surface feel forces which are acting downwards, net forces which are acting downwards, then this surface becomes curved and it becomes stretched. It is not a plane surface any longer, it becomes stretched surface, and this is because it experiences only weak adhesive forces from air molecules above it. Here is a stretched surface, and a force, inward force, acts on this surface normally. And what does this force do? It tends to draw the surface molecules in the bulk of the liquid. You see, there is a net force on these molecules, therefore, there is an attempt by the molecules to force them inside the liquid. This makes the liquid assume the shape of having the least surface area. You see, I showed you the curved surface, this curved surface. This curved surface is such that it has least surface area, and it makes the surface behave like a stretched elastic membrane, a rubber sheet for example, which is stretched, so that it becomes difficult to push an object through it. The surface of water, for example, behaves as if there is a membrane on it, and you can place certain things on it, as we shall see, and they would not fall, they would not go through it. The stretched surface stores energy as potential energy, because work has been done by the residual forces in stretching it. You see, since there is a force acting on it, it stretches, and therefore, this stretched surface stores energy, because work has been done in stretching it. The surface energy per unit area is expressed as the surface tension of the liquid. You see, take the water surface for example, it is stretched and the energy per unit area is represented by surface tension. If we wish to increase the surface area, we will need energy, because increased surface area would require greater energy to store. This implies that external forces must work against internal surface forces to increase the area. There is another way in which the surface tension is defined. Suppose you have a liquid surface and you draw a line on it, then perpendicular to this line, normal to this line, the force per unit area is defined as surface tension, and the units of surface tension are therefore Newton per meter, Newton by meter, because the force is per unit length and it acts along the length of this line which I have drawn. Let us try to understand the concept of surface tension through an example. I have told you that the surface of a liquid is stretched, so that little things can be placed on it and they do not go through it. So, you can float a steel pin on the surface of water. To do this, you will have to slightly grease the pin. The pin depresses the surface a little, as I have shown here. The red surface is the depressed surface because of the pin placed on it, and the force, I said, acts along the surface. So, the force, these forces, they act along the depressed surface and they act all along the length of the pin. And if the length of the pin is L, small l, then on this side there is a force F L, on this side there is a force F L. The total force therefore acting on the pin is 2 F L, F L in this direction and F L in that direction. And you can take the vertical components, the horizontal components will cancel, the vertical components F L cos theta plus F L cos theta, they are in the upward direction, and therefore, they can support the mass of the pin or the weight of the pin m g. So, this force 2 F L cos theta acting upwards can support the weight of this pin, and the pin can float on water. Let us take another example. ABCD is a frame with BC as a movable arm. BC is movable, it can move this way or that way. A film is formed on the frame, say a soap film or some such thing. Because of the surface tension force, the film tends to shrink. See, why does it tend to shrink? I have told you that there is the film has surface energy and it is a potential energy, and the potential energy always tends to become minimum. So, therefore, there is a force to shrink this film. However, if you apply a force from outside, say force F, which is equal to the force which makes it shrink, then the film will stay in equilibrium. And what is this force? This force is S along the length L, S L, and since this film has two surfaces like this, one here or one above one below, the two surfaces, therefore, the total force acting is 2 S L. So, if you apply this force 2 S L from outside, then the film will stay in equilibrium, it will not shrink or it will not expand. In fact, you can do this experiment, you can make this frame vertical and then you can support a weight m g, which will keep the film in equilibrium, and this weight is m g equal to 2 S L. Therefore, the mass of the body that is supported is 2 S L by g. Let us take another example. Suppose this film is stretched by a length delta x, that means the area, new area created is delta x times L. So, the film is stretched and the area increases by L delta x, and since there are two surfaces, the area increases by 2 L delta x, and if you multiply by the surface tension S, then the work done is 2 S delta A, L delta x becomes delta A and the work done is 2 S delta A, and the surface energy of the film is increased because I have told you surface tension is the surface energy per unit area. So, if the area increases, the energy will increase, and by how much would the energy increase? It will increase by W, which is the work done. Now, show you a few common phenomena that you can observe. Here I have shown you a picture where I floated a pin on the surface of water. I told you, you slightly grease the pin, apply a little oil and then try to place it on the surface. I think the better idea would be to place it on a piece of this by paper handkerchief, so that the paper handkerchief will go down and the pin will float on the surface. There are animals, small animals called water striders, which can float on water, which they can walk on water in fact, as it is said. Here is this water strider. They are actually small water bugs which live on surfaces of ponds, slow moving streams and marshes. They can walk on water. The surface tension of water supports their weight. If you look carefully, you will find that the surface of water, which is called meniscus in a beaker, is curved such that it is concave towards the air above it. You see, if you place liquid in a beaker, then you see that surface is like this. It is concave towards air and convex towards water, and this surface is called meniscus. Why does it happen? It happens because of adhesive forces between the glass and water molecules. They are stronger than the forces between water molecules themselves, so that the molecules of the glass are able to pull the water near the wall of the container, and this makes this surface which is concave to the air and convex to water. Here I explain this in greater detail. This is a wall and these are molecules near the surface of water, and this is the surface of water shown in a expanded manner. And these molecules, you can see these molecules have surface force S between them, and these molecules they have slightly larger force. So, that there is a net force trying to pull the molecules on the surface towards the glass and upwards. Instead of water, if we take mercury in a beaker, then its surface is convex towards air. You know, remember that the surface of water was concave towards the air. The surface of mercury is convex. Why? Because the forces between molecules of mercury themselves are larger than the forces between molecules of mercury and glass. Here is another phenomenon which you must have seen very often. You fill a glass with water, let us say. When the water reaches the brim, the water, and if you add little more water, it does not overflow. Why? Because surface tension is able to support the slight extra weight of water. What happens is that since the glass is full, the surfaces which were pulling the surface up, the forces of glass molecules, they are now much weaker, because the surface, the water has already reached the brim, and now if we add little more water, the surface tension of water will be able to support. In fact, you can keep on adding little water and you will see how much water it can support. But what happens if we add a spoonful of detergent to this glass full of water? The water now starts overflowing. Why? Because the detergent lowers the surface tension of water. In fact, detergents are meant to reduce the surface tension of water, so that they can penetrate the soiled portions of clothes we want to wash. If you look at small drops of water, very small drops of water, or let us say on a glass plate, they are spherical. Why are they spherical? because their other forces are neglected, then the surface area must be the least, and sphere is the shape for which the surface area is the smallest. So, these little drops, they assume spherical surface, spherical shape. But if the drop is slightly bigger, then the other forces cannot be neglected. For example, the force of gravity cannot be neglected, and therefore, instead of being spherical, it still tries to keep the surface which has least area, but it is slightly flattened shape that the drop assumes. This also you must have seen many times. In fact, if you take a large drop of water or any other liquid and you break it up into a large number of smaller droplets, what happens? For example, when you spray something on your body, you feel the cooling effect. Why is the cooling effect there? You see, the volume remains constant. This big drop is being broken up into a large number of small drops. So, the volume remains constant. So, you can equate 4 pi by 3 r cubed. R is the radius of the large drop, and n is the number of drops, small drops which are produced. So, it is 4 pi by 3 n r cubed, and from this you can get r. And now, the surface area of the smaller drops is 4 pi n times r squared, and if you substitute the value of r in terms of capital R, you see that the surface area is now n to the power 1 by 3 r squared. That is, if n increases, the surface area increases. So, when a large drop is broken up into a large number of small drops, the surface area increases, and the energy for this increase comes from the drop itself, and therefore, you feel a cooling effect. You can do the opposite. You can have large number of small drops and coalesce them into a large drop. In this case, the surface energy decreases because the surface area decreases, and therefore, some energy is released, liberated, and it is released. Water has very high surface tension, which prevents it from soaking into pores and soiled areas of clothes. You see, these clothes have soiled areas and water cannot enter because of high surface tension. If you add soap or detergents, then they bring down the surface tension of water, and the water can go into these soiled areas and clean. Earlier times we used to heat water before washing clothes. What does it do? If you heat water, the surface tension comes down, and therefore, it again helps in water going into the soiled areas and cleaning them. Disinfectants, they are also solutions which have low surface tension, so that they can spread on the cell walls of the bacteria and thereby disrupt their function. Similarly, antiseptic solutions which you apply on wounds, etc., they have lower surface tension, so that they can spread all over the wounds and other affected areas. Waterproofing chemicals are made to have low surface tension, so that they can spread and soak easily and effectively into nooks and corners. You see, suppose on a roof you want to do waterproofing, then these chemicals can go into nooks and corners and also into the holes or whatever is there, and prevent water from leaking. They can go into the pores of the concrete also. So, we will continue with this surface tension in our next lecture. In this lecture, we saw that surface tension is there because of molecular forces between the molecules of liquid itself. These are called cohesive forces, and these forces keep the molecules intact and in equilibrium. In the last lecture, we were talking of surface tension. We learnt that surface tension is caused because the molecular forces acting on molecules on the surface of the liquid, they are not all balanced, and therefore, the liquid surface is stretched, and this stretched surface has a force along it called surface tension. In this lecture, we shall talk of angle of contact, and then we shall find the excess pressure into drops and bubbles, and we shall also see the capillary rise of liquids. Start with angle of contact. You see, if this is the vessel in which water is contained, this is the water surface, there is air above it, and then if I draw a tangent to this surface, then the angle between that tangent and glass wall is called the angle of contact. You see this one is the angle of contact, and it is conventionally measured through the liquid. Here again there is water, there is air, and this angle, if I draw a tangent to the surface, this angle is the angle of contact, and it is measured through the liquid. And the angle of contact does not depend whether this beaker is straight or tilted, it does not matter. The angle of contact between water and mercury, for example, in the case of water, the angle of contact is about 30 degrees. If you take mercury, then the surface is like this, as we have discussed in the last lecture, and the tangent is like this, and therefore, the angle of contact is this, measured through the liquid. And this angle of contact, the mercury and glass and air, is about 130 degrees. Here again you see the same thing, there is a mercury drop on the glass plate, and this angle is the angle of contact. The angle of contact determines whether a liquid will wet a surface or not. Let us take glass, for example. If water is able to spread on glass, it will wet it. If it is not able to spread, then it will not. And the angle of contact determines whether the liquid can wet the solid or not. And if the angle of contact is less than 90 degrees, it will wet, and it will wet more if the angle is smaller. If the angle of contact is larger than 90 degrees, then it will not spread on the solid, and therefore, it will not wet. Soaps and detergents, as we discussed earlier also, are made to have small contact angles, so that they can spread over soiled surfaces of clothes. If we go by the angle of contact, if it is less than 90 degrees, then the liquid will wet. In the case of mercury, it is more than 90 degrees, and therefore, mercury will not wet. So, what happens to mercury if it falls on a glass plate? It will break up into small spherical drops. Let us know a few more things about the angle of contact. Angle of contact decreases when a soluble impurity is added to water. Say you add salt or sugar which is soluble in water, then the surface tension or the angle of contact decreases. Angle of contact decreases when water is heated. When you heat water, the angle of contact decreases. As said above, the angle of contact involving solids and liquids is an indicator of the wettability of the solid by the liquid, whether the liquid will be able to wet the solid or not. This is an interesting case. Surface tension causes liquids to form bubbles and drops, and these bubbles trap air. As you know, if you must have played with soap bubbles, they trap air inside, and this trapped air can become a source of oxygen for some organisms. There is an organism called water spider, and this water spider is a species which always lives underwater. So, how does it get oxygen? It carries with it a bubble held by hair on its abdomen and legs for its own supply of air. It is just as you are going to Mount Everest carrying a cylinder of oxygen with you. It is obvious that the pressure inside drops and bubbles will be higher than the pressure outside. Otherwise, they will be crushed by the pressure from outside. If you have played with soap bubbles, you will remember that you have to blow air or apply pressure to break a drop into bubbles. That is the source of excess pressure inside a bubble. But how much higher is the pressure inside? Let us calculate. Suppose we have a bubble here, and Pi is the pressure inside and Po is the pressure from outside, and R is the radius of this bubble. Now, since the pressure inside is higher, it keeps pressing on its surface and tries to expand the surface. Let us say the expansion takes place by delta r. Then the increase in volume because of this increase in radius delta r is 4 pi r squared delta r, and the work done in this process is 4 pi r squared delta r into P, because P times dV, Pi times Po, the pressure difference times dV is the work done, and therefore, the work done is 4 pi r squared into pressure difference into the increase in the radius. Recall that the surface tension is also defined as the surface energy per unit area. So, if S is the energy per unit area, then the extra surface created creates extra energy which is stored in the surface. And what is the extra energy? That is equal to delta W. And what is the extra energy that is required is S times delta A, where delta A is the extra surface created. And what is delta A? Delta A is delta times the total or the derivative of the total surface area, that is 4 pi r squared. So, this delta A is 8 pi r delta r. So, we have the equation, the work done 4 pi r squared into the pressure difference into delta r is equal to the S delta A, that is S times 8 pi r delta r, and from this equation we get the pressure difference, that is Pi minus Po, P inside minus P outside is 2 S by r. That means, the inside pressure is in excess of the outside pressure by an amount delta 2 S by r, where r is the radius of the drop. Bubble will have two surfaces, one inside, one outside. Therefore, the increase would be 4 S by r for a bubble, because there are two surfaces, inside surface, outside surface. For the drop, there is just one surface, and therefore, the excess pressure is just 2 S by r. By a similar process, we can show that, in fact, I explained to you that the surface of water is concave upwards, and we can show that the pressure on the concave side is higher than the pressure on the convex side by the same argument that we just carried, and the excess pressure is 2 S by r. That is, pressure on the concave side is higher than the pressure on the convex side by 2 S by r. I have just explained that the pressure inside a drop is in excess by an amount 2 S by r, where r is the radius of the drop, and a bubble has two surfaces, one outer, one inner, and therefore, the excess pressure inside a bubble is 4 S by r. Suppose we have water in a beaker, and there is a drop of water on just touching the surface, and there is a bubble just inside. What happens? You see, remember, the bubble inside the liquid has only one surface, that is the inner surface. Therefore, the excess pressure inside the bubble, which is inside the liquid, is 2 S by r, because inside the liquid bubble has only one surface, and this drop also has pressure which is greater in the inside by an amount 2 S by r. If they are of the same size, then the excess pressure inside is the same in a drop near the surface and in a bubble near the surface. If you have two bubbles, one smaller, one larger, bring them into contact by a nozzle or by a cork and open the cork, what will happen? You see, this is a smaller bubble, the pressure inside is higher because it is inversely proportional radius. So, it is higher pressure here and lower pressure here. So, the air will go into this, and this bubble will grow, and this bubble will actually become smaller in size. Now, let us assume that there is a bubble somewhere inside the liquid at a depth h. So, what is the pressure outside? The pressure outside this is the pressure of atmosphere on the surface plus the pressure of this liquid column, which is h rho g. So, the total pressure outside this bubble is h rho g plus the atmospheric pressure P atom. What is the pressure inside? The pressure inside must be higher by an amount 2 S by R. Therefore, the pressure inside is 2 S by R plus pressure outside, that is 2 S by R plus H rho g plus the atmospheric pressure. And from this equation you can calculate the depth at which a bubble of a particular radius would be in equilibrium. Suppose you have a nozzle. This is a question which is asked many times. You have a nozzle and you want to create bubbles inside water, and the radius of the bubble is given. What kind of pressure you would acquire to create those bubbles? So, it is very simple. The nozzle must create the required excess pressure. When you blow into the nozzle should create necessary extra pressure inside the bubble. And what is that extra pressure? It is equal to 2 S by R. So, you can calculate what extra pressure you need. Just plug in the values of S and R and you will find that you require, in this case, 72.7 Newton per meter square pressure inside the nozzle to be able to create bubbles of this size. This is very interesting and this is discussed in very few textbooks. You see, you have a liquid placed in a beaker or some other vessel and you dip a glass plate, a glass slide for example, and when you want to take this glass slide outside water, you want to pull it up, then what happens? As you pull it up, the surface of water clings to the surface of glass, and this is what happens. When you pull it up, then the surface becomes like this along the glass plate. That means, the force of surface tension would act downwards along the length of this, and the periphery of this or the total length is twice width plus the thickness, 2 W plus T, that is the total length which is in contact with water. S is the surface tension of water, and therefore, the force required is twice W plus T into S. You see, understand this. Normally, we say that the force of surface tension is along the surface, and we think it is along the horizontal surface. It is not always so. In this case, the surface of water has become like this, and therefore, the surface is acting down, the force of surface tension is acting downwards, and it is acting all along this periphery of the slide, which is 2 W plus T. And if you multiply this by the surface tension, then this gives the force which is required to pull this glass plate out of water. You see, this is our common experience, that when a narrow glass tube is dipped in water, the liquid rises in the tube. On the other hand, in a glass tube dipped in mercury, the liquid level goes down, it gets depressed. This phenomenon is called capillarity. That is, if you dip a glass tube in water, the water rises. If you dip a glass tube in mercury, then the mercury surface gets depressed, as shown here. What is the reason? What causes this phenomenon? Let us try to understand. You see, I explained to you the meniscus of water is concave upwards, and I also explained to you the angle of contact theta. Now, this is concave because the molecules in the glass wall, they attract the molecules of water near the wall and they get pulled upwards. Suppose the net adhesive force, net force between the glass molecules and the water molecules is T. Then this force T pulls the water molecules upwards and gives this shape to the meniscus. I show you in expanded form. These are the molecules on the glass wall. These are molecules very near the glass wall, and if they are in equilibrium, then this force T, that is the net force due to the adhesive forces, must be equal to the force of surface tension if these molecules have already assumed the shape concave shape, there must be an equilibrium, and this T must be equal to S. Now, the vertical component T cos theta, here this vertical component is T cos theta. This T cos theta pulls water up, and T we have seen must be magnitude wise must be equal to S. So, therefore, the force pulling the water molecules up is the rim has a perimeter 2 pi r. So, it is 2 pi r and the force is S cos theta. Therefore, this is the net force trying to pull the water upwards, and if the water rises to a height h, then it has pressure h rho g, and the force is into the area of cross section of the tube, which is pi r squared. So, we have these two forces which keep the water in balance, and from these two equations we get h is equal to 2 s cos theta by r rho g, where rho is the density of water and r is the radius of the tube. So, for ordinary silica glass and water, the contact angle is essentially 0, is very small. Therefore, the above relation becomes this relation, cos theta becomes equal to 1, and therefore, it becomes h equal to 2 s by r rho g. Notice that if the contact angle is greater than 90 degrees, then h becomes negative. That means, instead of the liquid rising, the liquid gets depressed, it goes inside the tube. Now, there is another way in which this can be explained. You see, you have again a vessel containing water and a tube dipping into it. The pressure at this level, at the same level, must be equal. We know all that the pressure in a liquid at the same height is always equal. So, pressure here is all equal, and here the pressure is atmospheric. Therefore, the pressure at this inside the tube at this level is also P. Pressure from outside, which is acting on the water column, is also the atmospheric pressure, and we have seen that this pressure is larger than the pressure on the convex side, and it is this difference of pressure which pulls water up. P outside is atmospheric, P inside is 2 s by r. So, this is the total pressure, P minus 2 s by r. Add to this the pressure of this column, which is rho g h, and for this to be equal to P, it is obvious that rho g h must be equal to 2 s by r. That is, h must be equal to 2 s by r rho g. Again, pressure outside is P, inside is P minus 2 s by r, and if you add to that the pressure of this column which has risen, then the pressure of this column inside becomes P minus 2 s by r plus rho g h, and this must be equal to P. So, if you this can happen only if 2 s by r is equal to rho g h or h is equal to this. Same thing happens with mercury. The only difference is that the mercury goes down in the tube rather than going up, and this equation can also help us in determining the surface tension. In fact, in laboratories this method is used to determine the surface tension of water. What you do is you dip a small tube and then measure the rise of the liquid column, measure the radius of the tube, and then use this equation S equal to h r rho g by 2, and you will get the surface tension. There is a question here. In an experiment in the laboratory, a capillary tube of diameter 2 millimeter was dipped in water. The water rose in the capillary to a height of 1.5 centimeters. Find the surface tension of water. So, just apply this formula and plug in the values. H is given, rho is given, g we know, r is given. Therefore, you can find S, and S for water is 0.073 joule meter square. You know, remember, surface tension is energy per unit area. So, joule by meter square. In the next lecture, we shall take other properties of liquids such as viscosity and see its effects.
dear students, we have studied till now about the long distances of transport in plants. Today, we are going to discuss the topic, the uptake and transport of mineral nutrients. Carbon dioxide is taken from the atmosphere, the water is absorbed by the soil. But how does the mineral ions are uptaken? This is exactly what we are going to study in this lesson. So, the uptake of mineral ions take place by active absorption, where energy is used in the form of ATP. The reasons, what are the reasons of being active absorption? Number one, the present as charged particles, and second, the concentration of ions in soil is lower than in roots. Now, let us focus on the key concepts of active absorption. The first, the specific proteins in membranes of root hair cells pump ions from soil into cytoplasm of epidermal cell. Secondly, transport proteins are embedded in plasma membrane of endodermal cells. The active absorption of mineral ions can be well explained in the following diagram. In the first step, you can see an ATP driven pump that transports hydrogen ion out of the cell. In the second, the electrochemical gradient causes potassium ions to enter by way of a channel protein. And the third, negatively charged ions are transported along with hydrogen ion into the cell. After the active absorption of ions, let us see how the mineral ions are translocated. The important features of translocation here is the one, it takes place by transpiration stream. Secondly, there are chief sinks in the plants. Let us see what are these chief sinks. Apical and lateral meristems, young leaves, developing fruits, and storage organs. In plants, the mineral ions can be mobilized or immobilized. So, in the case of the mobilization of mineral ions, they are mobilized from older to younger leaves. Second, before leaf fall in deciduous plants. And thirdly, the elements which are mobilized, they are phosphorus, sulfur, nitrogen and potassium. In plants, the food is transported through phloem. The food is prepared in the plant in the form of sucrose. This sucrose is transported from source to sink. Now, what is the source? The source are the leaves where the plant synthesize food, and sink the storage organs where the plant and the food is used. The most important form of food prepared in the plant is sucrose, which is transported from source to sink. What are these sources? The sources are the leaves where the sucrose is initially prepared in the form of starch, gets converted into sucrose and then transported to the sink, that is the various storage parts of the plant body. Second important point is the phloem transport is bidirectional movement, unlike unidirectional in xylem, because in plants the food is prepared in the leaves and then it is transported to the various parts of the plant body. Now let us see that what does the phloem sap contains. The phloem sap, it contains water, sucrose, amino acids and hormones. The bidirectional movement in the plant body can be well explained in the following diagram. The diagram shows the root absorbed by the root hair is transported to the leaf, and the food is prepared in the leaf by the process of photosynthesis in the form of starch. The starch gets converted into sucrose and is transported into the various storage parts of the plant body. Now, you may wonder that how the phloem transport food, what are the experimental evidence? Yes, we have an experimental evidence that which is called the girdling experiment. A ring of bark is removed from the woody stem. The upper part is attached to the lower part by central xylem. Look into the picture. In this girdling experiment, what do you observe? You observe the accumulation of food material just above the ring, and the roots die out. In the following figure, you see the girdle, the bark which is removed, and here the accumulated materials. So, what do we conclude? We conclude the removal of phloem cuts food supply to roots. So, what is the inference? That the transport of substances take place through phloem. Now, let us see what is the mechanism of phloem translocation. It is explained very well by a hypothesis which is called manch flow hypothesis, which postulates that the movement of protoplasm in massy along a turgor pressure gradient induced by water potential gradient. This particular hypothesis can be explained by a model which is as follows. This model is called mass flow model. If you look into the picture, the model consists of two reservoirs A and B, one containing the concentrated solution, other containing the dilute solutions which contain sugars. Now, what is observed in this model? We observe the water flows from B to A and the turgor pressure increases. So, what is the result? The increased turgor pressure causes mass flow of sugar from A to B. In the same way, in living plants, we can also explain the transport of substances through phloem, as the glucose is prepared at the source, that is the mesophyll cells of leaves. It is converted into sucrose. The sucrose is loaded into sieve tube cells which form sieve plates, and the loading of phloem set up water potential gradient that facilitates mass movement in phloem. So, to conclude, we can see the pressure flow hypothesis, that is, looking into the following figure. Physiological process of loading sucrose into sieve element at the source. The pressure flow, phloem and xylem are coupled in an osmotic system that transports sucrose and circulates water, and the physiological process of unloading sucrose from sieve element into the sink. So, to conclude the topic, we see that the translocation of substances through phloem take place by pressure flow hypothesis, where we have two concepts, source and sink. The prepared food is in the source and it is transported to the sink, that is the different storage parts of the plant body. Thank you. Have a nice day.
Hello students, in today's session we are going to discuss the process of photosynthesis in higher plants. Before that, let me tell you children, we should appreciate presence of plants and trees around us. In totality, the plant kingdom is really important for us. Of course, it gives us food, shade, many other things in addition to oxygen, which we definitely require for our respiration. So, what this photosynthesis is? This is the process by which the plants will make their own food and also food for us. In addition, will give us oxygen also. Oxygen and food, and also for shelter we use plants, plant material to make houses and other things. Coming to the food first, the tree is making food through photosynthesis. that means tree is able to use light as energy to make its own food. Think of the food chain which is operating on this earth. Food chain on earth begins from sun, then comes the tree, and after tree or vegetation will come the first organism which will eat the food produced by plant, and then other animals which have eaten on these animals. For example, if wheat is produced in the field, now wheat plant had taken sunlight through photosynthesis and produced the food in the form of wheat grains. Now this wheat grain is suppose eaten by rat, then rat was eaten by cat, cat was eaten by dog, and dog is eaten by some other bigger animal. All these are placed in the food chain one after another depending upon who is eating whom. But if you try to understand in detail, whatever the point of eating food may be there, but eventually it is coming from sun. Suppose cat has eaten the rat, then rat had eaten wheat, and wheat was coming from plant, and plant could make it through sunlight. So what I am trying to make you understand, children, is that photosynthesis is the process which makes it possible for food chain to run on earth and also food web. Coming to photosynthesis, this is a process where plant will use carbon dioxide, water in the presence of sunlight, will convert it to starch which is stored in the plant, and it is glucose is stored as starch and oxygen is given out. We have to understand the process, how it is happening, how oxygen is produced, what is the source of oxygen in this reaction. First of all, this is possible in plant only in green areas, especially leaf, which has pigment which can trap sunlight. But yes, any part of the plant which is green in color may be able to perform this activity of photosynthesis to some extent, but we know that main green part of the plant is leaf. Photosynthesis, which is a physico-chemical process. Physical because physically light is trapped into the plant, and chemical because chemical reaction is taking place for production of food and oxygen. And it is only possible in case of green plants. You can see in this slide that food we can get only for plant. Only green plants can enter into the process of photosynthesis, and as I told you, it is a physico-chemical process, and use of light energy is must. Presence of sun is must. Please appreciate the presence of sun in our system. And synthesis of organic compound will mean synthesis of food in the plant, which is in the form of carbohydrate. With this background, we move forward to understand the process of photosynthesis. For photosynthesis to occur, the major requirement is sunlight, which plants are trapping from sun, then the carbon dioxide which we are giving out in our respiratory process, we are taking in oxygen, giving out carbon dioxide, and then water. As is shown in this diagram in this slide, the water is absorbed by plant roots and it moves towards the leaves, towards the apex of the tree. So, it is available in the leaf. Carbon dioxide is absorbed from atmosphere, and when these two items are available, that is H2O water and CO2 carbon dioxide, in the presence of sunlight, it is converted to glucose or carbohydrate C6H12O6 plus oxygen O2. What is the source of oxygen in this? Is it H2O or is it CO2? Because both the items are having oxygen. it is proved beyond doubt that the source is water. The oxygen which is given out by plant, which we use for respiration, the source is H2O and not CO2. So, these are the basic requirement for photosynthesis which are met with. If one of the three is not available, then photosynthesis is not possible. That is why during the night time, when sun is not there, photosynthesis will not take place. At this point of time, children, I would also like you to know that plants also do respiration like we do. And as far as respiration is concerned, whether it is plant or whether it is animal or whether it is you, we take in oxygen, we give out carbon dioxide. That means plants, while doing respiration, are taking oxygen and giving out carbon dioxide, and while doing photosynthesis, taking in carbon dioxide and giving out oxygen. Now, try to relate it with plant day and night conditions. During daytime, when sun is available, definitely photosynthesis is going on and plant is consuming carbon dioxide and giving out oxygen. Then plant is taking oxygen for respiration and giving out carbon dioxide also. This is happening during the day. Now, what is happening in the night? Plant is doing respiration, taking oxygen, giving out carbon dioxide, but not doing photosynthesis. So, not taking carbon dioxide and not giving out oxygen. During daytime, if you sit under the tree or go under the tree or go in a garden or in a forest, you feel fresh because there is more oxygen than the carbon dioxide. Of course, plant is taking little bit of oxygen for respiration and giving carbon dioxide, but the same plant is using the same carbon dioxide for photosynthesis and giving out lot of oxygen. But if you are sitting under the tree during night, after some time you will feel suffocated or disturbed or little difficult. Why? Because now plant is not giving out oxygen, it is only giving out carbon dioxide because it is only doing respiration in absence of sunlight, no photosynthesis. That is why it is advised that do not go to garden or forest in night and do not sleep under the tree during the night time. In this diagram, you can see that there is a plant, the roots are shown which are absorbing water from soil and carbon dioxide is taken from atmosphere, and there is sun, the light of which is trapped by the leaves and photosynthesis is going on. So, children, now this is a time to understand the photosynthetic machinery. We know photosynthesis is important and it is going on in a green plant, but how? Also we know that sunlight, water and carbon dioxide are required for photosynthesis, but then we must know how this is made possible. First step is trapping the sunlight, and that is achieved by plant by chlorophyll. The chlorophyll which is present in chloroplast in the leaf, that chloroplast is doing this job of trapping the sunlight. Once light is available, then carbon dioxide is made to come inside and the light reaction proceeds, results into the formation of starch. I think I am repeating this part that glucose or carbohydrate is stored in plant in the form of starch. In photosynthesis, the plant is making carbohydrate. So, children, we have understood that sunlight is the main basic requirement for photosynthesis. The next point to understand is carbon dioxide, which is another requirement for photosynthesis to occur. Certain simple experiments were done in past to confirm this fact. As the diagram shows, there is one bell jar, in that there is one candle burning and there is one rat alive. Rat is trying to breathe with the oxygen available in bell jar. Now, this candle is burning using the oxygen in the bell jar. So, oxygen is being used by two, by burning of candle, by this rat in respiration. Now, rat is also giving out carbon dioxide and candle burning is also giving out carbon dioxide. After some time, carbon dioxide will accumulate in bell jar. So, rat will die because rat is not getting oxygen to breathe, and candle will also not burn any further because candle is not getting oxygen to burn. This experiment proved that for respiration we definitely need oxygen and we are giving out carbon dioxide, and any burning process oxygen is consumed and carbon dioxide is given out. Using this information in the background, one more experiment was planned. In the bell jar, one candle burning, one rat alive and one small mint plant. Now, if you use your past knowledge, the rat is utilizing oxygen for respiration, giving out carbon dioxide. Candle is using oxygen for burning and giving out carbon dioxide. Now, this mint plant, it is consuming this carbon dioxide given by rat and the candle and giving out oxygen instead. So, in the second bell jar you can see the rat did not die and candle also did not stop burning, because oxygen was made available to candle and to the rat by this mint plant. By this, two things were proved: that carbon dioxide is definitely required by plant for photosynthesis, and in turn plant is definitely giving out oxygen. So, utility of carbon dioxide for photosynthesis was proved, not only for photosynthesis, also for our livelihood, because we can't go on producing carbon dioxide and then live in that carbon dioxide atmosphere. We need oxygen, and for that we need plants. Children, try to understand value of plants around you. Without that we cannot make our life possible. So, children, we have discussed part of photosynthesis in the plant kingdom. We have also appreciated the presence of plants around us and the basic requirement for photosynthesis, which are sunlight, carbon dioxide and water. We have understood that plants are source of food on earth for food chain and for our respiration, and also for cycle of oxygen on earth. Life of animals and human is impossible without the presence of plants. In the next episode, we will discuss how chlorophyll helps in the process of photosynthesis and where chlorophyll is exactly present in the leaf and what is the mechanism of light and dark reaction. With this, we come to the end of this session. Thank you. Dear students, in previous session we discussed about photosynthesis, its need for the plant and for the organisms, and also its requirement. We did talk about chlorophyll, which is important part of photosynthetic machinery in the plant. We know that photosynthesis primarily takes place in leaves with the help of pigment chlorophyll and of course sunlight, water and carbon dioxide. Leaves are green, but we should not feel that photosynthesis will take place only in leaves. Whichever part of plant is green in color can participate in the process of photosynthesis. This will also mean the part of the plant which is not green will not do photosynthesis. That means plant is synthesizing food through photosynthesis for plant itself, especially the parts which are not green, and also for us. So, photosynthesis becomes very important. First thing, we get food through this for plant and for ourselves, and then we also get oxygen for breathing. Coming back to chlorophyll, the pigment, which is an important pigment for photosynthesis. It is present in a structure called chloroplast. We know in the leaves there are mesophyll cells in which we have chloroplast, and these chloroplasts will have chlorophyll, and they have capacity to orient them or align them in such a way in the leaf so that they get maximum sunlight when sun is there. We know the purpose why they do it, so that they are able to participate in the formation synthesis of food in the leaf. From leaf, this food will travel to different parts of the plant, the green parts as well as non-green parts. And when fruits come on this tree, perhaps we will also use those fruits as food material for us. When we are discussing about chloroplast, it is important for us to know the structure of chloroplast. You can see in this diagram, there are areas called grana, stroma, and there is membranous structure, stromal lamellae, grana, membranous lamellae, and of course, there is grana which is having fluid grana. In the chloroplast, there is very clear division of labor, which part will do what. The membranous part, as I told you just now, the lamellae, they will help in trapping the light, bringing light in, using it for the production of ATP and NADH. In the chloroplast, there is very clear division of labor. Which part will do what is decided. There is no overlapping. The membranous part, as I told you, the grana lamellae and the stroma lamellae, they do the job of trapping the light, the sunlight, and helps in the formation of ATP and NADPH. Whereas the fluid stroma, it will bring carbon dioxide in. This carbon dioxide is going to help in photosynthesis and going to help in the formation of food. The glucose, which is eventually stored as starch granules in this chloroplast only. Now, the first reaction which I talked about, bringing in sunlight through lamellae and synthesizing ATP and NADPH, this is called light reaction because it is taking place due to entry of light. The other reaction, bringing in carbon dioxide, is normally called dark reaction, not because it is taking place in dark, it is not taking place in dark. It is taking place in the presence of product of light reaction ATP and NADPH. So, light is even responsible for dark reaction because product of light reaction is being utilized in dark reaction. It is only called dark reaction, but it is also dependent on light reaction. Anyway, bringing in carbon dioxide, the remaining part of photosynthesis, making of or synthesis of glucose is called dark reaction, and this glucose is stored as starch, the starch granules which are also present in the chloroplast. Later on, this food material will be transported in different parts of the plant. So, we have discussed the structure of chloroplast and chlorophyll. Now, let us talk little more about chlorophyll in detail. Chlorophyll is a pigment involved in photosynthesis. There are many pigments present in the plant like chlorophyll A, chlorophyll B, xanthophylls, carotenoids. Before I explain you these pigments, let me just tell you that when you look at any plant, you will find so many leaves, and leaves have different shades of green or sometimes different shades of yellow. In the same plant, you have leaves having different shades. Why it happens and how it happens? Because chlorophyll A is bluish green in color, whereas chlorophyll B is yellowish green, xanthophyll is yellow, and carotenoids are yellow to yellow orange. Now, depending upon which pigment is present in which part of the leaf or the plant, you will find that particular color. But eventually it is chlorophyll A which is basically involved in photosynthesis and helps in the synthesis of food in the plant. Children, so far we have discussed about chloroplast and the chlorophyll, the pigments. Also, we have known that chlorophyll A is the major pigment for photosynthesis and chloroplast has important role. We will now see the structure of chloroplast in this diagram on the slide. You can see the stroma, you can see grana, the lamellae of grana and stromal lamellae as well. Stroma has lamellae as well as fluid stroma. Whenever it is lamellae, it is membranous. We can even see inner membrane and the outer membrane. Membranous part of chloroplast will trap sunlight and will help in the formation of ATP and NADPH, whereas fluid grana, as I have already discussed, will help in bringing in carbon dioxide. So, this hugely membranous structure within chloroplast helps in trapping sunlight inside the cell for the purpose of photosynthesis. This is the structure of chloroplast and we have discussed about different types of chlorophyll, and now we move on to understand the light reaction. Light reaction, which is basically synthesis of ATP and NADPH, has some steps. It is photochemical reaction or photochemical phase. Children, why do we call it photochemical phase? Photo means light, chemical means some chemical reaction going on in this phase. So, bringing in sunlight makes the photo part and chemical reaction going on inside the leaf makes the chemical part. We know that 6 CO2 plus 6 O2 in the presence of sunlight will make oxygen and glucose C6H12O6 plus 6O2. That means this chemical reaction is also important, where you are converting carbon dioxide and water to glucose and oxygen. Both we require so much, glucose as food for plant for us and oxygen for respiration for plant and for us, and that is the reason this is called photochemical phase. Now, this photochemical phase has certain steps. You can see on the slide, there is light absorption, there is water splitting, there is oxygen release, and then there is synthesis of ATP and NADPH. You all know, children, that whenever I say ATP, I mean energy. Energy requirement is equal whether it is plant or any organism or human. And when energy is utilized, then this ATP is converted to ADP and again it is converted to ATP by chemical reactions. So, first step is light absorption. Light absorption has so many facets. First thing, sun should be there, sunlight should be there, the ray of incident should be correct, the exposure of plant or tree to the sunlight should be enough, and position of leaves should be correct, the mesophyll cells and the alignment of chloroplast within the leaf should also be in a proper direction. When all this happens correctly, then light is absorbed, and once it is absorbed, definitely it reaches the chloroplast, because it is chloroplast membranous area which is bringing light in. So, that is light absorption. Coming to water splitting. Water is basic requirement for photosynthesis, no doubt about it, but unless it splits, to hydrogen and oxygen, the chemical reaction cannot proceed. This oxygen is very important for this chemical reaction, and of course, hydrogen will be forming electron which will run through electron system, which we will discuss in the next session. So, splitting of water will also take place within the plant tissue, especially the leaves. Coming to oxygen release. During this chemical reaction of photosynthesis, the oxygen is released. That is one important part. Carbon dioxide is taken in and oxygen is released. If oxygen was not released, then purpose of photosynthesis could not be served, and in that case we could not have any life on earth, because even plants need oxygen for respiration. We also need, but plants in respiration, they also take oxygen and give out carbon dioxide. It is only for photosynthesis that they take carbon dioxide and give out oxygen. They have added quality which helps life to sustain on earth. An end product is ATP and NADPH, for which this whole system was operating. Now, we will further see in the following slide and the following diagram how this light is being trapped. Dear students, I will now explain to you the light harvesting complex, which is present in the leaf and works like antenna to take light in. It is also in short called LHC, light harvesting complex. It has basic point near the base. There are pigments, large number of pigments with protein molecules. Then it has photostem 1, which is called PS1. You can see in the diagram photosystem 1 or PS1 and photosystem 2 or PS2. The interesting thing to note is that in these two photosystems, chlorophyll A molecule is not there, pigment is there, but chlorophyll A molecule is not there, and chlorophyll A molecule is present only in the lower part, where you can see one molecule circled red called photon. In fact, this chlorophyll A pigment present in the base will absorb light, but primary acceptor is chlorophyll A, but the total system works to allow chlorophyll A to work. That means, photosystem 1 and photosystem 2 will together work as antenna, light acceptor system, and then it is absorbed by chlorophyll A, which is present in the lower area. I will now show it in the diagram. You can see there are pigment molecules at the base shown by green color. It is having one chlorophyll A molecule which is showing as photon, the red line, and this is in fact the reaction center, whereas the photosystem 1 and photosystem 2 are making the primary acceptor part acting like antenna, and electron system plays a role in this, which we are going to discuss in the next session. So, children, this is the light harvesting complex which plays an important role in photosynthesis. In today's session, we have discussed about the structure of chloroplast, its functioning, the division of labor in chloroplast. We have also discussed about 4 types of pigments: chlorophyll A, chlorophyll B, xanthophylls and carotenoids, and the colors imparted by them. We also discussed about chlorophyll A, which is the primary pigment for photosynthesis, the light reaction, the dark reaction, the production of ATP and NADPH, and also we have understood the role of light harvesting complex in photosynthesis. With this, we come to the end of this discussion. Thank you.
राजघाट महात्मा गांधी का समाधि स्थल है। जहां पर उनकी यादों को हमने संजो कर रखा है। उनके जीवन के आखिरी पड़ाव राजघाट पर हम उन्हें एक श्रद्धापूर्ण नमन करना चाहते हैं।
ईश्वर अल्लाह तेरू नाम, सबको सुमति दे भगवान। रघुपति राघव राजा राम, पतित पावन सीताराम।
राजघाट दिल्ली में स्थित है। यमुना नदी के पश्चिमी किनारे पर यह समाधि स्थल है। यहाँ काले संगमरमर से बनी समाधि पर गांधी जी के मुख से निकले अंतिम शब्द हे राम उद्धृत किए गए हैं। देश विदेश से आए लोग यहाँ आकर श्रद्धा से गांधी जी को नमन करते हैं। गांधी जयंती के अवसर पर राजघाट पर विभिन्न कार्यक्रम आयोजित करे जाते हैं।
पहाड़ी पर चढ़े और बैठ गए। उनके शिष्य उनके पास आए और वे यह कहते हुए उन्हें शिक्षा देने लगे, धन्य है वे जो अपने को दीनहीन समझते हैं।
ओम पूर्णमदं पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य
महात्मा गांधी के इस समाधि स्थल पर निरंतर जल रही ज्योत उनकी उपस्थिति का आभास कराती है और उनके सुनहरे भारत की कल्पना को साकार करने की हमें प्रेरणा देती है। राजघाट में यादों को संजो कर रखा है हमने। श्रद्धा के फूल समर्पित हैं उनको, करते हैं हम उनको शत शत नमन।
You know that electricity is a flow of electrons through conductors like wires or PCBs and is quite similar to the flow of water in some respects. All conductors have free electrons. These free electrons are loosely held to the atoms and therefore can move freely from one atom to another. The movement of these electrons is usually random. However, if a force in the form of an electric voltage is applied across a conductor, all the electrons start moving in the same direction, resulting in an electric current. The electric voltage is just like pressure of water or air. More voltage, more current. An electric resistor is like an obstruction or a tap which decreases the current. Electric current can be a flow of electrons, always in one direction, in which case it is called a direct current or DC. Or it can be for a fraction of a second in one direction and then for another fraction of a second in the opposite direction, when it is called alternating current or AC. The dry cells give DC, and the power we use for the lights and fans is AC.
Can an electrical appliance work on AC as well as DC?
No. Normally, electronic gadgets like transistors, televisions, tape recorders are designed to operate on either AC or DC.
But some transistor radio sets can work on AC as well as DC?
Yes, indeed. But they have a battery eliminator built in, which converts AC into DC.
How does the battery eliminator do that?
By letting electrons move in one direction only. A semiconductor device called a diode allows us to do that.
What is this semiconductor diode?
A semiconductor diode is made up of a semiconductor metal like silicon or germanium, which are doped with some other elements like phosphorus or aluminum. There are two kinds of semiconductors, N-type and P-type. A diode is a piece of semiconductor which is on one side N-type and on the other P-type.
But how does it allow electron flow in one direction only?
It may be a bit difficult, so follow carefully. You know that everything is made up of atoms, and atoms are made up of electrons, protons, and neutrons. The electrons move around protons and neutrons, which are located in the center, like the sun in our solar system. A metal conducts electrons because the electrons which are farthest away from the protons and neutrons are loosely held to the atoms of the metals and therefore can move from one atom to another easily. In semiconductor elements, the outermost electrons are not so free, so these elements cannot conduct electricity easily. For example, silicon atoms have 4 such electrons, which are shared with other silicon atoms, as you can see here. Now, if some phosphorus atoms, which have 5 outermost electrons, are added to this matrix, then this one electron extra is more free and can help in electric conduction. This is called doping of silicon with phosphorus to make N-type semiconductor. To produce a P-type semiconductor, the semiconductor metal is doped with aluminum, which has only 3 electrons in its outer shell. This produces sites in the matrix which have 1 electron less. Such sites are called holes, which can be filled up with electrons. The holes in a semiconductor help in electric conduction by a different mechanism, as you see now. Here, as the holes move backwards, the electrons move forward.
I still do not understand how a diode conducts in one direction only.
I am coming to that now. As I have already said, a diode has a p-n junction, which means it is on one side p-type semiconductor and n-type on the other side. Now, if we connect a battery to the diode in such a way that the positive terminal of the battery is connected to the p-type semiconductor and the negative to the n-type, see what happens. The electrons from the negative terminal of the battery overflow the n-type semiconductor, and after crossing the junction, combine with the holes in the p-type semiconductor. The hole current is also in the same direction. So, there is a net flow of electrons from the negative terminal to the positive. That is, an electric current flows. But see what happens in case we connect the positive terminal of the battery to the n-type and the negative terminal to the p-type. There is no flow of current. Now you explain what happens if we connect an AC source to a semiconductor.
The diode will conduct when connected with forward bias, and it will not conduct electricity in the reverse bias.
Let us now see some diodes and understand what they do. See, this is a battery eliminator. The diodes are here. And here in this tape recorder, diodes are used to rectify AC into DC because the electronic circuit needs DC supply. The diodes we just saw in the battery eliminator and the tape recorder are called power diodes or junction diodes. They are all made up of silicon. They are used to provide DC power using AC.
How does one know which end is N-type and which is P-type?
These are the most common types of diodes used in electronics. Notice this silver or black band. The end near this band is the N-type semiconductor. In the other diodes, the upper end here is the N-type semiconductor.
Very interesting. But tell me, do diodes ever get damaged?
Yes, they do. If we apply excessive voltage to a diode, it may burst with excessive current, just like a pipe can burst if water at a very high pressure is passed through it. Each diode has a current limit, which the manufacturer specifies, and you can find out these limits from the data books. As you may guess, diodes which are used for high voltages like 100 volts or more are big in size, while the ones used for lower voltages are small. The diodes for larger currents normally have a metal casing. This helps to dissipate the heat generated because of the resistance of the diode.
What happens if a high voltage is applied to a diode in reverse bias?
Then also, the diode may burn out. In fact, one of the main specifications of a diode is its peak inverse voltage. Peak inverse voltage or peak reverse voltage is the maximum reverse voltage a diode can survive. It varies from 50 volts to 1000 volts or more. Now I will show you the other kinds of diodes. This is a point contact diode. It is made of germanium. It is used to filter or rectify communication electric signals which are AC. It is used in communication instruments like radio receivers and transmitters. See here, this is a point contact diode in this transistor radio. There are some special diodes also, which are for very special uses. They are made by different processes using different materials. Like this light-emitting diode. It is made of gallium and arsenic. It emits light when forward biased. They are used as displays for electronic clocks and instrument displays and level indicators in music systems. Then there are regulator diodes, also called Zener diodes. They look like ordinary diodes. They are used to regulate voltage, which means if the voltage from a source exceeds the desired voltage, then it lowers it.
How do they do it?
You see, any diode connected in reverse bias will start conducting above a certain voltage. In regulator diodes, this voltage is regulated by adjusting its chemical composition, so that the diode starts conducting at a lower voltage determined by its chemical composition. This results in a drop of voltage across the Zener diode to the desired level called the Zener voltage. Zener diodes are available for different Zener voltages. And different current ratings. The Zener voltage is generally printed on the diode body. Here you see a Zener diode used in a battery eliminator and in an audio amplifier. This is a bridge rectifier. It is made up of 4 power diodes connected to each other. It has 4 terminals and is also called a full wave rectifier because it gives rectified full waves. Then there are diodes for very special uses. Like the varactor diode used in communication circuits of television or VCR, they offer variable capacitance as is denoted by its symbol. Here, in this PCB of a demodulator circuit of a VCR, these are varactor diodes. Then there are diodes used in the AC power regulation circuits like SMPS of a color television. They are like two Zener diodes connected in parallel, opposed to each other. They can regulate AC just as the Zener diodes regulate DC. Here you see a photodiode. It is used to detect and measure light, for example, in a camera.
How can one test whether a diode is okay or not?
By using a multimeter or resistance meter. A burnt diode will show low resistance no matter which way you measure its resistance, while a good diode will show very high resistance when it is connected in reverse bias. This is all I have to teach in this program. Now let us recapitulate what we have learned. Semiconductor diodes are made of semiconductor metals like silicon or germanium. There are two kinds of semiconductors, N-type and P-type. N-type semiconductors are made by doping silicon with phosphorus, and P-type with aluminum. A diode is on one side P-type and the other side N-type semiconductor. Diodes conduct electricity in one direction only. They are therefore used to rectify AC into DC. There are different types of diodes: power diodes, point contact diodes, Zener diodes, varactors, light emitting diodes. A diode can be tested using a multimeter or oscilloscope. It shows low resistance when forward biased and high when reverse biased. Diodes are used in almost all electronic equipment.
मित्रों, आपको हमारे कार्यक्रम कैसे लगे? आप अपनी प्रतिक्रियाएं और सुझाव हमें भेज सकते हैं। हमारा पता है किशोर मंच, CIET NCERT, श्री अरविंदो मार्ग, नई दिल्ली 110016। आप अपने सुझाव हमें ईमेल द्वारा भी भेज सकते हैं। हमारा ईमेल पता है ciet.kishormanch@gmail.com।